Hi everyone, welcome to PrepFusion. So now we are going to see some basic terminologies. So whenever you see a particular question based on semiconductor physics, so these terms will be again and again used, like average collision time, effective mass, mobility, drift velocity, drift current density. So these terms will be again and again introduced there. So we will see the basic meaning of these terms and we will see the formula of these terms. Okay. So first one is average collision time. So what is the average collision time? So let's just say this was your semiconductor. This was your semiconductor. This is the semiconductor that you are having. In this semiconductor, silicon crystal. I am talking about silicon crystal. So silicon atoms are there, and these silicon atoms will be making the bond. So I am not showing the bond. I am just telling that these are the silicon atoms. Now it might happen that there would be some impurity. Let's just say I am talking about donor impurity. Now one electron is a free electron. Now if the current is flowing, that means this free electron needs to move. If the current is flowing, that means this free electron needs to move. But just as it started moving, the movement is not that smooth, right? Because there are atoms, and because of the temperature, if atom gets some temperature, that means they will be vibrating. I told you, if atom is getting some temperature, then it will be vibrating. If atom is getting some temperature, then it will be vibrating. So these atoms are vibrating. These atoms are vibrating, and this electron needs to work. This electron needs to move. Let's just say electric field is applied in this direction. So now this electron needs to move. But what will happen is that just as it will start moving, so since these atoms are vibrating, so it will collide these atoms. Or what may happen is that, like after a collision, it has reached here. Now what is this? This is your phosphorus atom, which is positively charged. Although the complete system is neutral, but phosphorus is positively charged because it has given some electron. That's why it is positively charged. So now let's just say it is working like this. Now what this phosphorus will do? This phosphorus will change the motion of this electron, because this is positively charged, and positive and negative, what they will do? They will repel each other. So it will change the trajectory. Like it cannot go here. It will change the trajectory. So basically, whenever an electron is working, it will collide with the atoms. It will collide with the atoms. It cannot move freely. So let's just say first collision happened at 2 seconds. The second collision happened at 4 seconds. The third collision happened at 7 seconds. So what was the average time here between two successive collision? Here the time between two successive collision is 2 seconds. Here the time between two successive collision is 3 seconds. So what is the average of 2 seconds plus 3 seconds? That is 2.5 seconds. So this average time is known as average collision time. So average time between two successive collision is known as average collision time, because when the silicon crystal is moving, when the electron is moving into the silicon crystal, it doesn't move freely. It will collide with the atoms, and since it is colliding with the atoms, and between the two successive collision there is a certain time. So when you take the average of all these certain times, then what do you get? You get the average collision time. So this is what have been written in complete theory. This is already written, a very simple term. With the term only you are able to understand the meaning. So what it is? It's the average time an electron or charge carrier travels freely before it collides with something, like it could be atom, or it could be impurity, or it could be other electron as well, because there would be a lot of electrons, no? There would be a lot of charge carriers. So it could be other electron. Impurity, I have already told. What do you mean by impurity? Donor atom or acceptor atom, right? So impurity also I have already told, and atom, because atom will be vibrating at their place because of the temperature. Okay, so analogy he has given. This is a very simple analogy, you can read on your own. So this is the average time an electron travels freely. Like average time electron travels freely, that means I told you that first collision happened at 2 seconds and second collision happened at 4 seconds. So between 2 seconds to 4 seconds it was moving freely, right? And third collision happened at 7 seconds. So between 4 seconds and 7 seconds it was moving freely. So it was moving freely for 3 seconds and 2 seconds. So 3 plus 2 divided by 2, so average time was 2.5 seconds. So it was moving freely for 2.5 seconds. So your average collision time is 2.5 seconds. Or you can define it as the average time between two successive collision. That is known as average collision time. Okay, very simple thing, very simple thing. And this line also you will be able to relate. If collision time is more, what does that mean? First collision happened at 2 seconds. Second collision happened at 10 seconds. That means it is able to move freely in a better manner. Electrons are moving in a better manner. If electrons are moving in a better manner, electrons are moving more freely, what does that mean? Conductivity will be high. Because I told you, for the conductivity, electron has to move. And if they are moving more freely, what does that mean? conductivity will be high, right? So high collision time means higher conductivity. Okay, so very simple thing, very easily you are able to relate. No one will ask you the definition, but in the examination, if it is mentioned that average collision time, that means you should be able to understand what is the meaning of average collision time. You will see, okay, collision, electrons will be colliding. So between two successive collision, what is the average time? That is known as average collision time. And if the time is larger, that means between two successive collision, electron is moving more freely. If electron is moving more freely, that means conductivity will be high. Very simple thing. Let's go to the next term, that is effective mass. This is important. Here we are going to study effective mass on a very surface level only. Okay, in a very crude way, I will tell you the meaning of effective mass, but again it will come back when we study direct band gap semiconductor and indirect band gap semiconductor. So at that time it will again come back. As of now, you will just understand in a very easy manner and you would be already knowing the meaning of it. Let's just say I am having a mass of 75 kg and I am moving with the velocity of v. I am having a mass of m moving with the velocity of v. Then what will be my momentum? M into v, right? Or what would be my kinetic energy? That would be half mv square. So this formula, who gave this formula? Newton gave this formula. So these formulas I am able to apply because this mass is decent enough. 75 kg, very good mass. Here also 75 kg, very good mass. 60 kg, 1 kg, 2 kg, very good mass. Like this is classical mechanics. This is mechanics only, no? So this is classical mechanics. Here mass is decent enough. But when it comes to electrons, what is the mass of electron? 9.1 into 10 to the power minus 31 kg. And now if my electron is moving with the velocity of v, let's just say my electron is moving with the velocity of v. So what will be its momentum? Mass of electron into v? No. So classical mechanics doesn't work on these particles, these small particles. So that's why we have to introduce the concept of effective mass. So me star I will put. Now what is this effective mass? So let's just say an electron is moving freely and other electron is moving in a silicon crystal. One electron is moving freely, other electron is moving in this silicon crystal with respect to the applied electric field. Along with that, there could be some impurity as well. This impurity, if it is a donor impurity, then it will repel the electron. If it is a acceptor impurity, then it will attract the electron. So here the movement and here the movement, both movement will be different because here it is moving freely and in this silicon crystal there will be some hindrance as well, no? Like these atoms will be vibrating or there are impurities, the hindrance that I already explained, right? So this movement will be different and this movement will be different. Now I am saying that this electron is moving with the velocity of v and this electron is also moving with the velocity of v. So I will say momentum of this one will be mv and momentum of this one will also be mv. No, here the concept of effective mass will come into action. So when the electron is moving into a crystal, its effective mass is different than its actual mass. So this is the definition that has been written. Okay, so effective mass is the apparent mass of an electron or hole inside a crystal. So if you want to use the formula of classical mechanics, then in place of mass you need to put effective mass. Are you able to understand this point or not? Okay, if I want to use this formula of kinetic electric, if I want to use this formula of kinetic energy half mv square, then here in place of m I will put m star, in place of momentum I will put m star into v. Are you able to understand this point? So effective mass is the apparent mass of an electron inside a crystal. It is different from the actual mass because regularly arranged atom in the crystal changes the way electron and hole moves. They don't behave like a free particle in the empty space, so we assign a new effective mass that explains how easily they can accelerate under a force. Okay, so electron moving in a free space, electron moving inside a crystal, both are the different things. If both are moving with the velocity of v, still the momentum will be different. All good, all good, all fine. That's why we introduce the concept of effective mass. So effective mass of electron I will be showing by mass of electron, since it is effective, so me star, or sometimes I can show it by mass of electron is negatively charged particle, so mn. So sometimes I can use me, sometimes I can use mn. Okay, and what about mass of hole? Or sometimes I can use, since holes are positively charged particle MP star. So Mn MP star or Me Ms star, whatever I want to use, I can use. Okay. So you understood the meaning of effective mass. Like no one is going to ask you, these terms will be used again and again. That's why I'm telling you that you should be knowing the meaning of these terms. Again, effective mass will come into action, like all these formula we are going to use, momentum formula we are going to use, and then we are going to study the EK diagram. Okay. So there direct band gap semiconductor, indirect band gap semiconductor we are going to study. So again, this concept will come into action. Don't worry about that. Okay. What is mobility? Mobility, movement plus ability. Ability to move. So mobility tells how faster an electron or hole can move. Look, all these scenario I explained with respect to electron. So effective mass I explained with respect to electron, but same goes for holes as well. Here I talked about collision time of electron, but same goes for hole as well. No, hole is also a particle. Movement of hole means movement of electron only, but covalent bond electron. Movement of electron means movement of free electron. Movement of hole means movement of covalent bond electron. So when I am explaining everything with respect to electron, the same thing will go with respect to holes as well. Okay. So here I am explaining mobility. Mobility means movement plus ability. So ability to move. So mobility tells the ability of the movement of electrons or holes. Okay. So this is the definition I have been written. Mobility tells us how fast a charge carrier, it could be electron or a hole, can move when we apply an electric field. So whenever we apply an electric field, how fast that particular charge carrier will move. Now what is the relation between mobility, collision time and effective mass? So mobility is given by mobility of electron I am putting. Mobility of electron will be given by E, collision time of electron divided by effective mass of electron. And mobility of hole will be given by, what do you mean by E? In place of E, let's put Q. Q is the charge of electron. Here, Q is the charge of hole. For both of the cases, Q will be 1.6 into 10 to the power minus 19. Because what is the charge on the electron? 1.6 into 10 to the power minus 19 Coulomb. Mobility cannot be negative. So here you don't say that sir charge is negative, so I will put negative. No, nothing like that. So just remember Q2 by M. Q2 by M. Q2 by M. If you are writing for the hole, then Q2P by MP star. From now onwards, whenever you use mass, in place of using mass, you will use effective mass. Is that clear to you? And it makes sense as well, no? Because if tau is high, what does that mean? Collision time is high. Collision time is high means between two successive collision there is more time. If between two successive collision there is more time, what does that mean? Electron is moving more freely. That means movement of ability for the electron is high. What I am saying, if collision time is high, that means ability to move is high. What does that mean? Mobility is high. So tau is proportional to mu. What about effective mass? Let us say I am having a weight of 75 kg and some other guy is having a weight of 50 kg. So who will run faster? This 50 kg guy or 75 kg guy? 50 kg guy, right? Because it is having lesser mass. So if mass is lower, that means ability to move is faster. So lower mass, that means mobility more. So you can see that inverse relation is there. So you will remember the formula Q2 by M. Sir, how this formula came, forget about it. Just remember the formula Q2 by M. Okay. And I have just written that what all are what things. So Q is the charge of the carrier, tau is the collision time, and M is the effective mass of the carrier. What is the unit? Unit is centimeter square volt into second. Sir, do I need to mug it up? No. I will tell you another formula for the mobility. From that particular formula, you will be able to write down this unit. So as of now, for now you can remember it, but later on you will be able to write it down in a very easy manner. Unit is centimeter square upon volt into second. Okay. Later on I will tell you a formula. From that particular formula, you will be able to write down this unit very easily. So till this point, first we started with average collision time. Very simple thing. If average collision time is more, that means mobility is more. Effective mass. You already know what is the meaning of effective mass, that electron moving in a free space, that is different than the electron moving inside a crystal. So that is the effective mass. And if I want to use the classical mechanics formula, then I need to use effective mass. Mobility, movement plus ability to move. So how fast your electrons can or holes can move when you apply an external electric field. Formula is Q2 by N. Okay. Now let's not go to the next slide. Here only I will discuss. The thing is, mobility of electron will be higher than the mobility of holes. What I am saying, mobility of the electron will be higher than the mobility of holes. Why is that so? Let's understand. So let's make our silicon crystal again. Okay, this bond is there, this bond is there, this bond is there, and this bond is there. Okay, these bonds are there. At 300 Kelvin, what will happen? One of the electron will go into the free space and it will create a vacancy of hole. Now if I apply the electric field, so tell me which electron will move more freely. This electron will move more freely, or this electron will move more freely. This electron is still in the covalent bond, and this electron has other competition as well. This is also in the competition, this is also in the competition, other competition are also there, no? Like if this electron needs to move, then it will have to jump. If this electron needs to move, it will have to jump from here to here. But this is a free electron, it can move very freely. Basically, one thing is between, this is the valence band and this is the conduction band. One electron from here has gone here and it has created a vacancy of hole. Now this hole is there and these electrons are there. Now let me know which electron will move more freely. This electron, it is alone, it is free, it can move very fastly. But this electron, for this electron in the competition, these electrons are also there, no? Are you able to understand this point? That means if this electron goes here, then this hole will become here. Basically, what I am saying is that this electron moves here. That means moment of hole will be there. For the hole to move, this covalent bond electron needs to move. If the covalent bond electron is moving, that means hole is moving. So for the hole to move, this covalent bond electron needs to move. And now you are saying that this covalent bond electron will be having tougher path than this free electron. That means this free electron is moving more freely. That means this free electron can move very fastly. And whenever I say free electron, that means electron only. And whenever I say covalent bond electron, that means I mean hole. So whose mobility will be higher? So mu n will be greater than mu p. So mobility of electrons will be higher than the mobility of holes. So whenever I say electrons, I mean free electron. Whenever I say hole, I mean vacancy of electron which was there in the covalent bond. So whenever I am saying that holes are moving, that means covalent bond electrons are moving. So covalent bond electrons will move with the hindrance, but free electrons will move more freely, right? So this is the theory that I have written. You will remember always that mobility of electrons will be higher than the mobility of holes. Say yes or no. So this is the theory that has been written. Holes are the missing electrons. A hole is not a practical particle, it is just the absence of electron in the valence band. To move a hole, neighboring electrons have to jump into the empty spot, right? But electrons are free movers, right? Electrons are free movers. Electron in the conduction band can move directly when pushed by an electric field. They don't need any other electrons to move out. Okay. So basically, here for the holes there is a lot of competition. For one hole there is a lot of competition of electrons. But for a free electron there is no competition. They can move freely. So mobility of electrons will be higher than the mobility of holes. Understood? Very simple thing. Let's go to our next point. What is this drift velocity? So drift velocity also we have already seen. This was our semiconductor. In semiconductor there was a free electron, there was a hole. So what we did? We applied a voltage. Because of the voltage there was an induced electric field. Now because of this electric field, this electron was moving and this hole was also moving. So this would be moving with the velocity. This will also move with the velocity. But they will move, but in between there will be collisions, right? Because this is the silicon crystal. So if this electron is moving, or if this hole is moving, then there will be silicon atoms, and because of that there will be collision. So velocity will not be constant. So let's just say sometimes velocity was 2 meters per second, then velocity became 3 meters per second, then velocity became 1.2 meters per second because of the collisions. So when you take the average, that average could be constant. So that is known as drift velocity. So it is the average of the velocity of your charge carriers when they move with respect to the applied external electric field. So this is the definition that has been written. So when you apply an external electric field to a conductor or semiconductor, electron starts moving in a specific direction. Same goes for hole as well. But electrons are constantly bouncing randomly because of the collision with the atoms. Their average speed in the direction of electric field is known as drift velocity. So it is the average speed, because you tell that sir electrons cannot move with the constant speed, that I know. But drift velocity, whenever I say drift velocity, although there is no word of electric field here, sorry, there is no word of average here. Whenever you write down drift velocity, in this word drift velocity, can you see anything called average? No. Average drift velocity we do not call it. We call it drift velocity only. But you should know that drift velocity is the average velocity of the electron or holes. Okay? Because velocity cannot be constant, but average velocity can be a constant number. Right? So what do you think? Drift velocity will be proportional to what? Applied field, right? So drift velocity will be proportional to the electric field. Electric field. So whenever the drift word would come into action, whenever the drift word come into action, drift means electric field. So till this point, if I ask you why the electron moves, when the electron moves, when you apply an electric field, and when you apply an electric field, drift velocity comes into action, and if electrons are moving, then current comes into action. So that current will be known as drift current. So whenever I say drift, in your mind electric field should come into action. Okay, drift means electric field, this should come into action. So your drift velocity Vd, drift velocity is proportional to applied electric field. When you remove this proportionality constant, so when you remove this proportionality sign, there would come into action a proportionality constant, that is mu, and that mu is known as mobility. Sir, mobility constant? We will see, don't worry. Okay, not in this lecture, but in the next lecture. But as of now, what you will say, Vd is equals to mu e. As of now, what you will say, sir, Vd is equals to mu e. So from here, mu will be Vd by e. Mu will be Vd by e. What is the unit of velocity? What is the unit of velocity? Meter per second. But here I told you distance will be centimeter, length will be centimeter, centimeter per second. And what is the electric field? Volt per centimeter, right? So centimeter per second into volt per centimeter. Centimeter goes upward. So this will be the unit of mobility. So Vd is equals to mu e. Till this point, only two formula is there. Mu is equals to Q2 by m. Vd is equals to mu e. But only formula is not important. The concept is also important. What is the meaning of drift velocity? Whenever I say drift, that means electric field. What is the meaning of mobility? Why the mobility of electrons is higher than the mobility of holes? What is the meaning of effective mass? Effective mass will again come into action. Average collision time also you know. So everything you know. All the formula is also clear. Vd is equals to mu e. Everything is crystal clear. Now you solve this question on your own. You should be able to solve. Electrons have an effective mass of m star equals to 0.2 m naught. Average collision time of 0.1 picosecond. Holes have an effective mass of 0.5 m naught. Average collision time of 0.15 picosecond. Applied electric field is 2 volt per centimeter. M naught is given, Q is given. Find the mobility. Mobility of electron and mobility of hole. So mobility of electron, what that will be? E2 by Mn star. 1.6 into 10 to the power minus 19. 2. Average collision time for electron is 0.1 into 10 to the power minus 12. By Mn star. Effective mass is 0.2. M naught, what is the value of M naught? 9.1 into 10 to the power minus 31. Yeah, one more thing you can see, what you can see, that here you have seen that mobility of electrons is greater than mobility of hole, right? So if collision time is same, then effective mass of electron will be lesser than the effective mass of hole, right? If electrons are moving faster, that means their effective mass should be lower. But it is general case. This is also general case, not always true. It may happen that in some material, you will not study those materials, but in some properties, in some material, at a particular condition, holes can also move faster than the electrons. Effective mass of holes can also be lesser than the effective mass of electrons. So here what I will write down, generally effective mass of holes will be greater, right, than the effective mass of electrons. Why is that so? Because here also I have written generally, not always true, generally. In your case it will always be true, okay? But in the examination, in some questions, let's just say mu p is given greater than mu n. So at that time you will not say, sir, this question is wrong. No. Till this date, in all the questions, mu n has been greater than mu p. But in the examination, if mu p greater than mu n is coming, then just apply the formula and solve it. Yeah, we were solving this question. So whenever you solve a question of EDC, always take care of the unit. Here you have put the unit of Coulomb, right? Coulomb. Picosecond it was, but you have converted into second. So Coulomb and then second, and downward you have put kg. So all the SI units are there. So your answer will come in the 1 second. Picosecond, yeah. So your answer should come in which unit? Here unit I have written centimeter square upon second into volt. Sorry, centimeter square upon second into volt. So answer will come in centimeter square upon second into volt. No, answer will be in meter square upon second into volt. Are you able to understand this point? Here I have put second, here I have put Coulomb, and here I have put kg. So all the SI units are there, no? So if all the SI units are there, then the final answer will be coming in meter square upon volt into second, no? Are you able to understand this point? Okay. In the options, if the answer is mentioned in centimeter, then you will convert it into the centimeter. So let's solve it first and then check the answer, and then I will tell you how you can convert. So always take care of the unit, that I am telling. Whenever you solve the questions of EDC, always take care of the unit. So let me pause the video and solve it, or I can solve it directly as well, because 10 to the power minus 19, 10 to the power minus 12, what that would be? 10 to the power minus 31. So this and this will get cancelled. This would become 1 by 2. 1 by 2, 0.8. So 0.8 divided by 9.1. Answer would be 0.8 divided by 9.1. Right? 0.8 divided by 9.1. So 0.08791. Why I have written so many digits? Because it may happen that in answer is given in centimeter square. But as of now, since everything is SI, your answer is coming meter square volt into second. But answer could be given in centimeter square. So here if you need centimeter square, what does that mean? What is the meaning of centimeter square? That means 10 to the power minus 4. This centi is 10 to the power minus 2. If I am doing square, that means 10 to the power minus 4. So if I need to put centi here, that means I am multiplying with 10 to the power minus 4. That means I have to divide by 10 to the power minus 4 as well. Are you able to understand this point? Just the conversion I am telling you. Let me add another page. Nothing but the conversion I am telling you. 1 second, guys. Yeah, so this was the answer. Now I am converting, right? So meter square to centimeter square I am going. That means here I have multiplied with 10 to the power minus 4. Because centi is 10 to the power minus 2. Since there is square, so 10 to the power minus 4. I hope this much is clear to you. So if I am putting centi here, that means I have already multiplied with 10 to the power minus 4. So I will have to divide with the 10 to the power minus 4 as well. And now this 10 to the power minus 4 will go upward. So what will happen? It will become multiply with 10 to the power 4. So what will happen? 1, 2, 3, 4. So 879.12. What will be the answer? 879.12 centimeter square volt into second. Is that clear to you or not? You might be a third semester guy or fourth semester guy, that's why I am taking time. But if you are someone who has who has been in third year, then at least this much should be clear to you, right? How to convert into different units. Okay, so this is the mobility of electron that we are getting. Similarly, you can calculate the mobility of holes as well. So 1.6 into 10 to the power minus 19. What is the collision time? 0.15 picosecond divided by 0.5 m naught. So 5 into 9.1 into 10 to the power minus 31. So again here as well. So 1.6 into 0.15, 1.6 into 0.15 divided by 0.5 divided by 9.1. So 0.0527, 05274 meter square volt second. And if I need to convert into centimeter, that means 10 to the power 4 I will have to multiply. So 527.47 centimeter square volt into second. So this is your mu p I am getting. What they are expecting next? Drift velocity of electron and holes. So third, drift velocity of electron. That would be mu p into E. What is, sorry, drift velocity of electron. So let's write down VDN, drift velocity of electron, VDN. So mu n into E. So what is the answer you are getting? 879.12. 879.12. So this is in the centimeter square upon volt into second, and E value is also given in the centimeter, 2 volt per centimeter, right, into 2. So what do you think, what will be the answer? What is the unit of drift velocity? Centimeter, meter per second, but everything is there in the centimeter. Everything is fine, volt is fine, second is fine, volt is fine, here centimeter, centimeter. So answer will be meter per second, but no, centimeter per second, because I am using centimeter here. So 879.12 into 2. 879.12 into 2. So 1758.24 centimeter per second. That would be mu p into E. 527.47, and what is applied electric field? That is 2. So 520 1054.94 centimeter per second. There you go. These are the answers. Okay, let's solve. Okay, we will solve more questions, but as of now, let's talk about the conductivity. So you already know the meaning of conductivity. Conductivity is the ability of the current to flow, ability of a material that it can allow the flow of current. So conductivity tells us how easily a material allows electric current to flow. But for the conductivity, there is a formula. So that formula you need to remember. So that formula of conductivity is, here I am writing down N. N doesn't mean electrons here. Okay, N is the charge carrier per unit volume. Q mu. N Q mu. Just tell me one thing. If charge carriers are more, that means conductivity will be more. If mobility is more, mobility means ability to move. So if electrons are moving fastly, not only electrons, any charge carrier, it could be electron, it could be hole. So when I am writing down N here, that means I am meaning it could be any charge carrier. Okay, so N is the electron, N is the charge carrier, Q is the total charge, and mu is the mobility. So if mobility is more and number of charge carriers are more, what does that mean? Conductivity will be more. So always there is a proportional relation, right? So sigma is proportional to N, sigma is proportional to mu, and sigma is proportional, like charge on the charge carrier. Every charge carrier will have some charge. So n q mu. Just remember this formula. You have to remember the formula. First formula, mu was E tau by m. Q tau by m, you can say E tau by m. Second, Vd is equals to mu e. Third is sigma equals to n q mu. Derivation and all we are not seeing, but we have to memorize the formula because questions are asked on these particular formula. Very, very straightforward, very simple questions will be asked. Very simple question. So n q mu, just remember n q mu. Like in class 12th as well, you might have studied this formula. What is n, what is q, what is mu? So n is the number of charge carrier per unit volume and mu is the mobility of a particle. Right? Now what is resistivity? This resistivity word have you heard? Resistivity is just the reciprocal of conductivity. Resistivity is just the reciprocal of conductivity. So that would be 1 upon n q mu, where n is the charge carrier. It could be electron or hole. It could be electron or hole. If I am saying or, that means I will use the plus sign. And mobility, it could be electron or hole, anything, right? So n q mu you need to remember. And resistivity is resistivity is just the reciprocal of the conductivity. Now there is something called resistance. You might have heard this word, resistance. What is the formula of resistance? R is equals to rho L by A. Let's just say there is a material. Let's just say there is this material. Okay, I am making it in 3D. And now across this material, what you are doing, you are connecting a battery like this. Okay, you have connected a battery like this. So now the current will flow. The current will flow. The current will be passing through this particular area. No? So from whichever the area, let's just say this was the material. This was the material. And if I have applied battery, let's just say current is passing from this particular area. Or better example would be this book. This is the material. And I have applied battery here. So current is passing through this particular area. So this is known as cross section area. Okay. So cross section area is this. So this is your A. And what is the L? L is the length. So the length at which the current is passing. So current will be passing the complete length L. Cross section area will be this. This will be your cross section area. And rho is the resistivity. So resistance of this particular material will be given by rho L by A. Rho into L by A. Rho into L by A. This rho is a material constant. Like this rho will depend on the material. In the material, the number of charge carriers will be there. The mobility of charge carriers will also be there. So all these things is depending on the material. Like how many charge carriers are there in this material. So rho is the material constant. It will depend on the material. What is rho? Rho is just the inverse of conductivity. What is the formula of conductivity? N q mu. What is the formula of mu? E tau by m. Other formula, Vd is equals to mu e. That's it. 3 formulas till now we have remembered. Right? So you understood the meaning of cross section area as well. Next we need to study about drift current density. So what do you mean by current density? So current density is simply given by I by E. Current per unit cross section area. So let's just say this is a semiconductor material or any material which can conduct the current. If I have connected a battery of V naught having a length of L, what will happen? The current will flow. The current will be passing through this particular cross section, and this cross section I am calling as E. So this current I is passing this particular cross section with the length L. So current density which is given by J. So this is your current density. Current density. So current density which is given by J, that is I by A. So current per unit area. Current density J is the current per unit cross section area. And this theory is written that whenever an electric field is applied across a material, charge carriers, electron or holes, will start moving in a preferred direction. This the current caused by this directional motion of carriers is called as drift current. Drift current is coming because of the electric field. So this is the important part here. Again I will use different color of pen. The drift current is coming because of the electric field that you have applied. Now let's just say this semiconductor material or this any kind of material was having some electron and it was having the hole as well. What is the direction of applied electric field? Direction of applied electric field is this. Why is this? Because this V potential will reach here, this negative potential will reach here. Direction of electric field will always be from positive to negative. Electrons will move in the opposite direction to the electric field. That's why the current will be this, and holes will be moving in the direction to the electric field. That's why the current will be this. So this is the current because of the electrons, this is the current because of the holes. So what will be the total current? In plus Ip. So always current will be added up. It will never happen that until some other electric field comes, it will never happen that these current will be in opposite direction. In some cases, two currents can be in the opposite direction, but because of the electrons and because of the holes, the current will always be in the same direction, because you know that holes are nothing but the movement of electron only. So if electrons are moving from right to left, that's why the holes are moving from left to right. So this will be the total current In plus Ip. Okay, so just a simple thing that we have already studied, that only I explained here. So current density is J equals to I by A. Now you have studied Ohm's law, right? In Ohm's law, what was the formula? J equals to sigma E. Do you remember it? J equals to sigma E. So from here, two kind of formula you will remember. J is equals to sigma E, and I will be, J is I by A, so sigma will be, sorry, J is I by A, so I will be sigma E into E. So this is your drift current. This is your drift current. And from now onwards, I will write down J drift, I drift, J drift, I drift. Okay. dr means drift, dr means drift. So this thing only I am repeating. Drift current density and drift current for semiconductors. So same thing I am repeating. Again the same thing I will write down. There is electron, there are holes. Electric field is there in this direction. There was no need of this slide actually. Electric field is there in this direction. Electrons will move here. Electrons will move here. Holes will move here. So your drift current density will be given by J drift because of the electrons. I should write J drift because of the electrons plus J drift because of the holes. Okay. Now just tell me one thing. What will be this J drift? Sigma into E, right? So here I am writing sigma n because I will write down the conductivity because of the electrons, and then I will write down sigma P, and E electric field I will show by this sign. Electric field here also I have shown by this sign, because by this capital E we will be showing energy. That's why I will show the electric field by this sign. Sigma NE plus sigma PE. What do you mean by sigma n, sigma p? Sigma n is the conductivity of the electrons. So that would be n q mu n. What will be sigma p? That would be p q mu p into E. What is this n? What is this p? So let's write down. What is the n? Number of electrons per unit volume. Number of electrons per unit volume. What is the formula of sigma? Sigma formula is n q mu, right? What was n here? N was the charge carriers, number of charge carriers per unit volume. Now there are two kind of charge carrier. One is electron, one is hole, and because of both of them, the current is actually being added. Because of both of them, the current is being actually added. And I know the formula of J here. I know the formula of current density, that is sigma E. But here I am considering only the electrons. Here I am considering only the holes. So I am writing down the conductivity of the electrons. That means now my charge carriers will only be electron. Right? Q is the charge on the electrons and Q is the charge on the hole. So that will be same only, right? Charge on the electron is also 1.6 into 10 to the power minus 19 and charge on holes are also 1.6 into 10 to the power minus 19. Now don't say that, sir, I will put negative here. Current are being added, no, current are being added, so don't put negative here, right? So number of electrons number of electrons per centimeter cube, and what are P? Number of holes per centimeter cube. And what is mu n? Electron mobility. And what is mu p? Hole mobility. Right? Q is the charge, or Q is simply the charge which is 1.6 into 10 to the power minus 19 coulomb. E is the applied electric field. E is the, let's just say this was your V naught, okay, and the length was L. Length of this semiconductor was L, and applied potential was V naught. So E is the external electric field, which will be equals to what? dV by dx minus dV by dx, that would be V naught by L, right? So N was number of electrons per centimeter cube, P is number of holes per centimeter cube, mu n is the mobility, electron mobility, mu p is the hole mobility, and both of the both of the currents are added. Both of the currents are there in the same direction, that's why they will be added. So NQ mu, this formula is very important here. So here no new formula you are learning, only one formula is there, J equals to sigma E. Sigma is NQ mu. There are two kind of charge carriers, one charge carrier is electron, one charge carrier is hole. So because of them I can write down the current. So this is my complete drift current. Sorry, drift current density. What is this? Drift current density. This is your drift current density. Now if I want drift current, then what will be the formula? If I want drift current, so the formula will be J drift into the area, J drift multiply with the cross section area, there you go. This will be your drift current and this is your drift current density. So what will be this? This will be your drift current. Don't worry, these formula will come again and again. So don't feel like that, sir, how you will be able to remember. You will be able to remember, don't worry about that. Very simple thing where we started with, the first formula came here, Q2 by M. Very rarely it will be used, very rarely. Okay. Then VD is equals to mu E, it will be used. It will be used in a good amount, right? And then conductivity formula came. Conductivity was NQ mu, where N is the charge carrier, number of charge carriers per unit volume. Okay. Or here volume would be in centimeter only, so centimeter cube I have written. Mu is the mobility, Q is the charge. Resistivity is just the reciprocal of the conductivity. Resistance is R equals to rho L by A. Then current density is simply J is equals to sigma E, that is equals to I by A. So I will be equals to sigma E into A. What is sigma? NQ mu. So here N is the charge carrier which could be electron, which could be hole as well, right? And because of both of the charge carriers, the current is being added. That's why I added the current because of the electrons, the current because of the holes. So these are the formula. Let's write down the current for different kind of semiconductor, for intrinsic semiconductor, for N-type semiconductor, and for P-type semiconductor. Okay. So let's write down the current expression, but I need to drink some water because of the cough that I am having. So I need to take a break and then I will come back. You try writing it down, because for intrinsic semiconductor, what do you know? Number of electrons per unit volume will be equals to number of holes per unit volume will be equals to intrinsic carrier concentration, right? So you write down the formula, which formula you get. Yeah, welcome back. So let's write down the drift current density and drift current for intrinsic semiconductor. Okay, so in intrinsic semiconductor, what was the scenario? This was your intrinsic semiconductor. Here electrons are also there, holes were also there. If you apply an electric field, both will be moving in the opposite direction, and the current will be, for both of them, the current will be in the same direction, and so total current will be added, right? And in the intrinsic semiconductor, number of electrons were equal to the number of holes, and that was known as intrinsic carrier concentration. So number of electrons were equal to the number of holes, that would be equal to intrinsic carrier concentration, right? So what will be the drift current density? So drift current because of the electrons, drift current because of the holes. Drift current density because of the electrons, drift current density because of the holes. So drift current density is sigma into E. What is sigma? N Q mu. So N Q mu N into E. This is because of the electron, and P Q mu P into E. This is because of the holes. And since N equals to P equals to Ni, so what you can do? Niq mu N into E plus Niq mu P into E. So what you can see here? What can come common? Ni into Q into E, that can come common. So Ni into Q mu N plus mu P into E. Basically only difference is mu N and mu P. So this is your drift current density, and if I need to find the current, I will multiply with the area. So this is the drift current density for intrinsic semiconductor. Along with that, you know one thing, that your drift current density would be equal to the sigma, that means conductivity into electric field. So applied electric field is E, so this will represent the conductivity of intrinsic semiconductor, right? So this particular term, J equals to sigma E, right? J is equals to sigma E. So this particular term will represent the conductivity of intrinsic semiconductor. So your sigma I, conductivity of intrinsic semiconductor, would be given as, how will you remember? Sigma is equals to N Q mu. So Ni, here charge carriers are N and P. Charge carriers are electrons and holes. So Ni Q mu N plus mu P. Since both of the currents are in the same direction, so both will be added. So this will be the conductivity of intrinsic semiconductor. Okay. What about N-type semiconductor? So normal formula for everyone. This is the normal formula. In N-type semiconductor, what would be there? Majority charge carriers will be electrons. For N-type semiconductor, majority charge carriers will be electrons. But holes will also be there, no? So both particles are there. Holes are in the minority. Holes are in the minority, but surely they are there. Although they are in the minority, but surely they are there, right? NQ mu N into E, PQ mu P into E. And since number of electrons are much larger than the number of holes, so J drift will also be approximately equals to NQ mu N into E. Although this is the full formula, this is the approximated formula. Okay. For P-type semiconductor, full formula will be the same only, NQ mu N into E. Let's make the P-type semiconductor. This would be your P-type semiconductor, where everywhere holes will be there, but minority electron will also be there. Plus PQ mu P into E, right? But you know that P is much greater than N, so your J drift would be PQ. Like very simple thing. Just now formula has come into action, so don't feel like that, sir, this is difficult. Nothing is difficult. J equals to sigma E, sigma is equals to NQ mu. If you just remember that, your job is done. Let's see the formula that has been asked in GATE 2025 examination. So very simple question have been asked in GATE 2025 examination. What they are saying, intrinsic carrier concentration they have given, that means Ni value they have given, that is 2.5 into 10 to the power 16 meter cube inverse. Electron and hole mobility they have mentioned 0.15 meter square volt into second. Hole mobility they have mentioned 0.05 meter square volt into second. Intrinsic resistivity they have asked. What they have asked? Resistivity. I forgot to tell the unit of conductivity. What is the unit? It is Siemens per meter. Okay. This is the unit. And here what will be the unit? RA by L. So what is the unit of R? Ohm. What is the unit of meter square upon meter? So ohm into meter, right? Ohm into meter. So unit will be ohm into meter. This will be the unit. So what is this mean? This is simply what will be the unit here? 1 upon ohm into meter, because conductivity is just the reciprocal of resistivity. So 1 upon ohm into meter. Meter you are already writing downwards. So 1 upon ohm is maho, or you can call it Siemens. Okay. So Siemens and maho both are the same thing. So Siemens per meter you can call it, or ohm into meter is the unit of resistivity. Very simple thing. Let's go to our question. This was our question. What you need to find? You need to find the resistivity. What is the resistivity? Resistivity is simply the reciprocal of the conductivity. So when you think of conductivity, you will think that okay, both of the currents will be added. And what is the formula of the conductivity? NQ mu. NQ mu. What is the charge carrier here? For in both of the cases, n equals to p equals to ni. So I will remember that n equals to p equals to ni. So nq mu, ni will come common. Q will also come common. Nq mu will not come common. So that will be mu n plus mu p. There you go. This is the formula, and I will be able to write down the final answer. Now, when I will be solving the problem, I will see the options. In the options, is there any importance of 10 to the power 16 or point or anything? What I mean to say is that, let's just say I solved this particular question and my answer came 12.5. Will I be able to tick on option B? Surely. Like without even taking care of 0.05, I just solved it. Like here I need to take care because 0.15 and 0.05 I need to add. So it would be 0.2. So 0.2 multiply with Q, that would be 1.6 into 10 to the power minus 19, multiply with 2.5, and then I need to take the reciprocal. If I don't care about this point sign, like in place of 2.5 I am writing 25, in place of 1.6 I am writing 16. If I don't care about that and I get my answer 125, still very confidently I can click on option B. But what if in the options 1.25, 12.5, 125 was mentioned? So at that time I need to take care of the calculation. In the examination, if I need to solve the question faster, I would know that here my point would not matter because all the options are different. So I can solve it faster, but here I will solve in a correct manner only. So what is the correct manner? Correct manner is 1 upon Ni value is 2.6 into 10 to the power 16. Sorry, 2.5 into 10 to the power 16. Q value is 1.6 into 10 to the power minus 19, and mu n plus mu p will be 0.2. When you solve it, 1.25 will come out. This will be the answer. Okay, I can see. Let's check 1 by 8. Look, 2.5 into 2, that would be 5. 16 into 5 would be 80. 1 by 8, 10 by 8, what that would be? 1.25. Answer would come out to be 1.25. Here you can see 10 to the power minus 3, and this would be 10 to the power minus 4. 10 to the power 16 and 10 to the power minus 19, that would be 10 to the power minus 3. 10 to the power minus 3, 10 to the power minus 4, 10 to the power minus 5, and 10 to the power minus 6. So if it goes upward, so 10 to the power 6 divided by 25 into 16 into 2. So 25 into 16 into 2. So 25 into 2 will be 50, 50 into 16. So that would be 10 to the power 6 divided by 800. So it will not be 10 to the power 6, some error we are doing. Yeah, answer is required in kilo ohm into meter. Answer is required in kilo ohm into meter. Okay, so for kilo I need to keep aside 10 to the power 3, and 10 to the power 3 divided by 800. So what will be the answer? 1000 divided by 800. So answer would be 1.25, and this 10 to the power 3 will be kilo ohm into meter, because everything is in the SI unit. Here everything we are putting in SI unit. So what will be my answer? My answer will come out in ohm into meter, right? Here everything I am putting in SI unit. So answer will come out into ohm into meter, not kilo ohm, but you need the answer in kilo ohm. So that's why 10 to the power 3 will also come. So that 10 to the power 3 will go into kilo. So kilo ohm into meter. So answer will be 1.25. Next, another question I have framed, that applied electric field is 2 volt per centimeter. Cross section area is 1 centimeter square. You need to find the drift current. Drift current you need to find. So what will be the drift current? That would be into area. And what will be this? Sigma into E into A. What is the value of sigma? Sigma is 1 by rho. Here I should write down in this manner. So J drift, what is current density? Sigma into E, and we are talking about intrinsic semiconductor, so sigma I into A into E into A. What is sigma I? Sigma I is simply 1 by rho I. What is E? 2 volt per centimeter. But let's put everything in SI unit. Okay, what we are doing, let's put everything in SI unit. So 2 volt per centimeter could be written as 200 volt per meter, because centi is 10 to the power minus 2. If it goes upward, it becomes 10 to the power plus 2. So 200 volt per meter, and this could be written as 10 to the power minus 4 meter square, because centi is 10 to the power minus 2. So 200 into area 10 to the power minus 4 divided by rho I value, because sigma is equals to 1 by rho I. So E into A 1 by rho I. What is the value of rho I? Rho I value we are getting 1.25 into 10 to the power 3. So what is the answer you will be getting? 200 divided by 1.25. 200 divided by 1.25 into 10 to the power minus 7. So 20 divided by 1.25. I should have been able to do it without the calculator, but as of now I just want to depend on calculator only. So 20 divided by 1.25, 16. 20 divided by 1.25 is 16, right? And so 16 micro ampere, that is the current you are getting. So these are the answer. Okay, very simple thing. This was 10 to the power minus 4. I gave 1 10 to the power minus 1 to this one, so this became 20. 20 divided by 1.25, 10 to the power minus 3, and this also goes upward, so 10 to the power minus 6. So 16 microampere. Very simple equation, very straightforward. Let's solve this one. Electric field of 0.01 volt per meter is applied along a length of copper wire. This time they have given copper wire having a circular cross section of diameter 1 millimeter. So there is a copper wire. This is a copper wire. So semiconductor they did not give this time. This time they gave the wire, and this is having a circular cross section. Circular cross section. So can you find out the cross section area? Yes. The diameter is 1 millimeter. So what will be the radius? 1 by 2 millimeter. And do we need the area? Let's see that. Conductivity is given. I need to find the current. Yes. So J is equals to sigma E. I will be equals to sigma E into A. I have the value of conductivity 5.8 into 10 to the power 7. This is in SI, Siemens per meter, although there is no use of the unit. Electric field 0.01, right? And now the area. What will be the area? What will be this cross section area? That would be pi r square. So pi into r is 1 by 2, 10 to the power minus 6, because r value is 1 by 2 into 10 to the power minus 3, right? So 10 to the power minus 3 divided by 2 meter. So it would be r square. It is r square. So your radius is 1 by 2 into 10 to the power minus 3. So it would be 1 by 4 into 10 to the power minus 6 meter square. So pi by 4 into 10 to the power minus 6. So what is the answer you are getting? This is actually 10 to the power minus 2 only. So let's write down in it as 10 to the power minus 2. So 10 to the power minus 2, 10 to the power minus 8, this would become 10 to the power minus 1. So 5.8 into pi, 5.8 into pi divided by 4. So 4.5 you are getting, 4.55 we are getting, roughly around 4.6 we are getting, but 10 to the power 7, 10 to the power minus 1. And everything is in SI, so answer will be in amperes. From here you can see that answer will be 0.46 ampere. So very comfortably, very easily, these kind of questions are just free marks, right? So very easily you would be able to solve. Let's go to the next concept. So next we are going to understand mass action law. Very important concept, very important. So listen to me very carefully. Just keep your full concentration here. So now let's just say I am having an intrinsic semiconductor. In this intrinsic semiconductor, I know that number of electrons will be equals to number of holes, and that will be equals to Ni, right? So here I am telling that number of electrons is equals to number of holes, and that is equals to Ni, and I am saying that these are 10. So 10 electrons are there, 10 holes are there, and Ni value will also be 10. Now what I did the doping of a donor atom. I did the doping of a donor atom. So when I did the doping of donor atom, what will happen? Donor atom will give me electrons, right? Donor atom will give me electrons. So this value will go high. Let's just say because of the doping of donor atom, the number of electrons became 50. What I am saying, previously the number of electrons and the number of holes were same, 10, 10. What is the multiplication of both of them? 10 into 10, that is 100. This is the previous scene when it was intrinsic. Now what I am doing, I am making it extrinsic. So what I did the doping. I did the doping in a manner that at the equilibrium I am getting 50 electrons. I am getting 50 electrons. So number of holes will make sure that I will be that number such that this multiplication remains constant. What I mean to say is that whatever the previous number of electrons into number of holes were there, that will always remain constant at the equilibrium. At the equilibrium, somehow if I did some doping, whatever the process that I did, because of that process, if number of electrons have become 50, the number of holes will be 2 only. Like, sir, how it will happen? Already 10 holes were there. So what happened to those 10 holes? So what really happened was, let's just say there was electrons. Because of the thermal temperature, what you created? Holes you created. Oh, sorry. What I am doing? Yeah, because of the thermal temperature, these electrons are created here and these holes are created here, right? And then you did doping. Because of the doping, what really happened? Because of the doping, there was a donor energy level, and because of the temperature, you got electrons here, right? This was the process. And let's just say another hole I will make here because of the temperature. So these holes you are making because of the temperature. In the intrinsic carrier, in the intrinsic semiconductor, 3 holes were there and 3 electrons were there. And when you did the doping, these more electrons came into action. When you did the doping. Now you know that since electrons have been more, so number of holes should be less because multiplication should be constant. Previously it was 3. This was 3. Number of electrons were 3. Number of holes were 3. So 3 into 3. So multiplication should be 9 only. Now you are saying that for the 9 it would be tough to explain. Let's take 4. So previously number of electrons were 4. Number of holes were 4. Now what really happened? Number of electrons got increased. So number of electrons got increased. 8. So number of holes will be 2 only. So what really happened is that from here the electron will fall back. If the electron is falling back, what will happen? This electron and hole will recombine. What will happen is that from here electron will fall back. First what really happened? This was the generation. This is known as generation and this is known as recombination. So this generation and recombination process will go on, and it will go on till the point that this multiplication and this multiplication becomes similar. So at the thermal equilibrium, this multiplication and this multiplication will be similar. Is that okay for you or not? How the multiplication will become similar? Because whatever the generation was there, one electron went here. Because of that, electron and hole pair were generated. One electron and one hole pair were generated. But what may happen is that to make sure that this multiplication remains constant, one electron can recombine with the hole. The electron can fall back and it can recombine with the hole. So this vacancy will be gone and here free electron will also be gone. Are you able to understand this point? So number of holes has been reduced to 2 now. Previously number of holes were 3, but now it has reduced to 2. So always at thermal equilibrium. What is the thermal equilibrium? As of now you will understand thermal equilibrium is the constant temperature state. At a particular temperature, now the number of electrons and number of holes have been constant. This is known as thermal equilibrium. We will understand thermal equilibrium in detail, but as of now what you will understand that at a particular constant temperature, number of electrons and number of holes have been constant. So that is known as thermal equilibrium. So at the thermal equilibrium, the number of electrons multiplied with the number of holes will always be constant. So this is the theory that has been written and we will use it in the problems. You will be able to understand, don't worry. and this law is valid for any kind of semiconductor. Okay, so this is the complete theory that has been written. In a semiconductor at thermal equilibrium, the product of number of electrons and the product of hole concentration to the product of electron concentration will be constant. Okay, so when it was intrinsic, n was equals to p is equals to ni. So if I multiply n with p, what I will get? N is equals to ni, p is equals to ni. So what I will get? N into p is equals to ni square. So this is known as mass action law. So always electron concentration multiply with the hole concentration will be a constant number, that is known as ni square. Let's understand by a practical example. Let's just say in my silicon, my ni value was like what is this? Ni value when it was intrinsic, when everywhere silicon was there, at that time number of electron and hole pairs were 10 to the power 10. So number of electrons were 10 and number of holes were 10. So what was their multiplication? N into p is equals to ni square, that was 10 to the power 20. Now what I did the doping. I did the doping of donor atom, and because of that doping, now my number of electrons became 10 to the power 50. So what will be my number of holes? The number of holes will be 10 to the power 5, because 10 to the power 15 multiplied with 10 to the power 5 will be 10 to the power 20. So always we will make sure that number of electrons multiplied with the number of holes will be equal to ni square. Is that okay for you? Okay, so we will see a lot of questions, it will be clear to you, don't worry. So this law is particularly useful. Yeah, so this line is also very important. When I will be using this law, so I will be using this law to find out the minority charge carrier concentration. Let's just say in my semiconductor, electrons are the majority charge carrier. In my semiconductor, I am having n-type semiconductor. Let's just say I am having n-type semiconductor. So electrons are the majority charge carrier concentration. So for finding number of electrons, I will use some different formula that we will study. Don't worry about that. But for finding number of holes, I will always use this mass action law. Basically, by somehow I will find out the number of electrons. In my n-type semiconductor, first I will find out number of electrons. Okay, and then I will use this n into p is equals to ni square. Number of electrons I am already having, this value I will already know, I can find out the minority charge carriers. So this law is particularly useful to find out the minority carrier concentration if majority carrier concentration is already known. Okay, and is the electron concentration per centimeter cube, per centimeter cube, and this is also per centimeter cube. And this law is valid for both intrinsic and extrinsic semiconductors. Now there is another equation that is known as charge neutrality equation. So charge will always be neutral. Let's just say I am having some semiconductor. Okay, in this semiconductor I am doping donor atom as well and I am doping acceptor atom as well. Charge neutrality equation. Okay, so if I am doping donor atom, what this donor atom will give you? Positive charge and a electron. And what this acceptor atom will give you? Negative charge and a hole. So here what all are the positive charge? The positive charge are Nd plus and number of holes. And what all are the negative charge? Negative charge are Na minus plus number of electrons. Number of electrons I will represent n, and every of them is having the same charge q, which is 1.6 into 10 to the power minus 19. Let us say this is the ion I am having. What is the charge of this ion? 1.6 into 10 to the power minus 19 only, no? This ion 1.6 into 10 to the power minus 19. This is negatively charged, this is positively charged. 1.6 into 10 to the power minus 19. So in a semiconductor where I am doping donor atom as well and acceptor atom as well, so total charge will be equal, total positive charge will be equal to the total negative charge. Why is that so? Because all the materials are electrically neutral. This thing we have already seen, all the materials are always electrically neutral. So when I am doping Nd atoms, what is really happening with Nd? They are having 5 electrons. So since they are releasing this electron, they are becoming positively charged. And when I am doping Na, what they are having? They are having a hole. So what they will do? They will take a electron, and since they are taking the electron, they will be negatively charged. So this is the negative charge, and electrons are also negatively charged. So electrons are also negatively charged. So this Q and Q will get cancelled out. So Nd plus P is equals to Na minus plus N. So usually I will ignore this plus sign. Usually I will ignore this negative sign as well. So total positive charge is equals to total negative charge. That's it. So this is known as charge neutrality equation. So two things are there in the semiconductor. First one is at thermal equilibrium, number of electrons multiplied with the number of holes will always be constant. That is equals to Ni square. And in a semiconductor, the semiconductor will be electrically neutral. So total positive charge will be equals to total negative charge. Positive charge will be coming because of the hole and donor atom, because of the hole and the donor atom, and negative charge will be coming because of the electrons and acceptor atom. Okay, well and good. So this is something that has been written. A semiconductor is electrically neutral, so total positive charge is always equals to the negative charge. This includes electron holes and ionized dopant. Okay, ionized dopants. P plus Nd P plus Nd plus is equals to N plus Na minus. So N is the electron concentration, P is the hole concentration, Nd plus is the ionized donor concentration, and Na minus is the ionized acceptor concentration. All good. Now let's see where we are going to use it. So what we are going to do, now we are going to find the number of electrons, or basically we are going to find electron and hole concentration per unit volume in our semiconductors. In intrinsic semiconductor, you already know that number of electrons is equals to number of holes is equals to intrinsic carrier concentration, is equals to intrinsic carrier concentration. But what about N-type semiconductor? So in N-type semiconductor, who are the majority charge carriers? Electrons. And who are the minority charge carriers? Holes. Right? And in N-type semiconductor, you do the doping of a donor atom, right? It would be non-zero, but acceptor atom would be 0. So there are two kind of law. First law is mass action law. The mass action law will say that at equilibrium, the number of electrons I am representing by N. What is this? Concentration of electron. And this is concentration of a hole. At any point at a thermal equilibrium, the concentration of electron multiplied with the concentration of hole will be equals to Ni square. What is this Ni square? When it was intrinsic semiconductor, from intrinsic only you are making it N-type, no? So when it was intrinsic semiconductor, at that time, what was the number of electrons, what was the number of holes? That was equals to N equals to P equals to Ni. So number of electrons when it was intrinsic, that was Ni. Number of holes when it was intrinsic, that was Ni. But now you have done the doping. So now things will change. Number of electrons and number of holes will change. So those changed number of electrons are N, those changed number of holes are P. Another thing also we know, what is that? Charge neutrality. Charge neutrality equation. What is the charge neutrality equation? Positive charge is equals to negative charge. Now in this N-type semiconductor, you know that what is the scenario? This is the scenario, right? But holes are also there, right? So here there are donor atoms. Donor atoms are positively charged. Along with that, holes are also positively charged. That would be equal to negative charge. Negative charge is only because of the electron. There is no acceptor atom. This is the equation 1 I am having. This is the equation 2 I am having. Now from here, what I will find out? First I will find out the value of N. What I will find out? I will find out the value of N. Okay, so what I would do? This N remains as it is. In place of P, I will put N minus Nd. This is the equation 3. So I will use equation 1 and 3. Using equation 1 and 3. Equation 1 and 3. What I am getting? N into P is equals to Ni square. So what I am finding? I am finding the value of N. So P is replaced with N minus Nd. n minus nd, and that would be equals to ni square, right? So what you are getting, n square n into nd minus ni square is equals to 0. So this is the quadratic equation, minus b plus minus under root b square minus 4ac divided by 2a. So better I can write it down in this manner, nd by 2 plus minus under root, look, I have written under root 4 by 2. What will be the value? Under root 4 is 2, 2 by 2 will be 1. So can I write down in this manner, under root 4 by 4? Basically this 2 goes in the under root. If this 2 is going in the under root, how it will go? If 2 is going in the under root, so how it will go? As under root 4, no? So this has to be squared, right? So this 2 is going in the under root. So nd by 2 square, and here it would become ni square. Because 2 is going in the under root, so it would go as 4. So basically it is actually going as 4. When 2 is going in the under root, it is going as a 4. So nd square plus 4 ni square divided by 4. So it can be written as nd square by 4 plus ni square. So nd square by 4 can be written as nd by 2 whole square plus ni square. So this is the formula that I have written. nd by 2 whole square plus ni square. Now what do you think? Can I take the negative sign? If I take the negative sign, then what will happen? nd by 2 minus nd by 2 whole square plus ni square. This will be a positive value. This will also be a positive value. And these two values will be added. So this particular value will be surely greater than nd by 2. Only I am talking about this particular value. This particular value will always be greater than nd by 2, because nd by 2 square plus ni square. Let's just say nd by 2 was 4. So 4 square plus something you are adding. Let's just say it was 1 only. So what you are getting? 16 plus 1 under root 17. And here what you are getting? nd by 2 was 4 only. So 4 minus under root 17. What is the answer you are getting? Under root 16 is 4. So under root 17 will be somewhat greater than 4. So what will be the answer? Negative value, no? Which is not possible. Concentration cannot be negative. So that's why you cannot take a negative sign. So which sign you will take? Positive sign. Basically, if you take the negative sign, then concentration will be negative. So that's why I will take positive sign. So what is the answer you are getting? Plus ni square. This is the number of electrons that you are getting. Now someone would be saying that, sir, I will try to find out the number of holes also in the same manner. What I would do is that I will generate another equation. What I would do is that I will use equation 1 and 2. What I would do, sir, I would do using equation 1 and 2. So now in place of n I am going to put nd plus p. So in place of n, what I am going to put nd plus p into p is equals to ni square. Someone will be saying that, sir, I will be doing this process. Okay. So p square plus nd into p is equals to ni square, or minus ni square is equals to 0. So what will be the value of p? Minus b plus minus under root b square minus 4ac. So this will become plus upon 2a. Even if you take the positive sign or if you take the negative sign, always this value will be negative. If I take the positive sign, if I take the negative sign, then surely it will be negative, right? Minus 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 will be minus only. Even if I take the positive sign, minus nd plus under root nd square plus 4ni square. So this value will always be larger than this value. That means this will always be negative. This whole value is always negative. and it is not possible, right? If it is always negative, it is not possible, because how the concentration can be negative? I am saying that number of holes are minus 10 to the power 3. So number of holes cannot be negative, no? It has to be a finite number. Number of holes could be 1, 2, 3, 10 to the power 3, 10 to the power 17. It could be a finite, it has to be a non-negative number, right? So not possible. What does that mean? That means you cannot find the number of holes by using this method. That's why I said that this equation, mass action law, is used to find out the minority carrier concentration, So in n-type semiconductor, who is the majority carrier concentration? This is the majority carrier concentration. So if I have find out the majority carrier concentration, how will I find out my minority carrier concentration? So this was your majority carrier concentration. So what will be your minority carrier concentration? So you know that here what I will do, I will draw a line. So you understood why we cannot use these equations to find out the minority carrier concentration. Okay, so what I will do, n into p is equals to ni square. So number of holes will be ni square by n. So n value I will be already knowing. So number of holes will be ni square by n. So this will be your minority. Just I will write down minority carrier concentration. Okay. So for n-type semiconductor. So in conclusion, what I can see, for n-type semiconductor, majority is electron concentration and minority is hole concentration. So electron concentration is coming out to be Nd by 2 plus under root Nd by 2 whole square plus Ni square. Okay. Now in most of the cases what will happen, let's just say my Ni was 10 to the power 10. Like previously my number of electrons and number of holes were 10 to the power 10 when it was intrinsic. Now I will do the doping much higher than this one. I will dope 10 to the power 16. My donor atom, that means I am putting 10 to the power 16 phosphorus atoms. And I am saying that all the phosphorus atom will give you one electron. And all are ionized. That means this was your donor energy level and this was your conduction band. So all of these 10 to the power 16 atoms are reaching into the conduction band. This is what I am assuming. So what will happen? This Nd value is very larger than Ni, right? Are you able to understand this point? So in most of the cases what will happen is that Nd, if like this is the generalized formula that should be there in your mind. But in the 99.95% cases, what will happen is that usually Nd is much greater than Ni. So what you can do, you can ignore this part. 100 plus 1, what that would be? Roughly 100 only, no? Or 1000. 1000 plus 1, that would be roughly 1000 only. So what I can do, I can ignore this. So with respect to Nd, I can put Ni approximately 0, right? With respect to Nd, I can put Ni approximately equals to 0. So what will happen? Nd by 2 whole square and then under root. So whole square and under root will get cancelled out. Ni I am putting 0, so this is gone, and whole square and under root will get cancelled out. So what you will be getting? You will be getting Nd by 2 plus Nd by 2. What that would be? Nd only. So your number of electrons will roughly be equals to, electron concentration will roughly be equals to the number of donor atoms. Number of donor atoms which are ionized. What I am saying, let's just say I have put 100 phosphorus atoms. So 100 phosphorus atoms will give me 100 electrons, because 4 are making the bond and 1 is nearly free. Now out of these 100 electrons, how many will reach to the conduction band? So here we are assuming that 100% are reaching. Let's just say only 90% are reaching. So what will be the value of ND there? 90, not 100, right? So this concept I have already explained. Also I will pick some question as well. There complete ionization will not take place. So N is roughly equals to ND. And what is the minority carrier concentration? That was Ni square by N, right? So roughly what that would be equals to? Roughly that would be equals to Ni square by Nd. There you go. So this is for the N-type semiconductor. So this formula you should keep in mind. Other formula should be there in your mind, that is N into P is equals to Ni square. N into P is equals to Ni square. So from there P will come out to be Ni square by N. And what is Ni, what is N, what is P, everything should be there in your mind. Similar kind of analysis, the ditto same analysis you are going to do for P-type semiconductor. So all the equations, everything I have written, right? So what you are going to replace here, N into P is equals to Ni square. Who is the majority charge carrier? Who is the majority? P. Who is the minority? N. So for finding minority, what you are going to do? From here only I am telling N will be equals to Ni square by P. But for the majority, you are going to solve these equations. So what you will do? N into P is equals to Ni square. Now here, let's write down these equations again. For P-type semiconductor, negative charge and hole, negative charge and hole, negative charge and hole. Along with that, there will be electrons as well. Wait a second, guys. Yeah, so what I was saying, so this was your P-type semiconductor. So in the P-type semiconductor, what was the scenario? Acceptor atom was there, holes were there, acceptor atom, holes, acceptor atom, holes. So acceptor atoms are negatively charged particle. Plus, who else is negatively charged particle? Electrons. And who is the positively charged particle? That are holes. What you will find out? You will find out the value of P. So for finding out the value of P, what you will do? P is equals to, what you will replace? You will replace the value of N. So N will be equals to P minus Na. So solving equation 1 and 2, what you will get? Here only I am writing now. N will be replaced P minus Na into P is equals to Ni square. So, so similarly, this kind of equation you are getting. In place of N, you are just putting P. So P minus Na is equals to Ni square. The same kind of equation I am getting. So what will be the answer of P? So from here, answer of P will come out to be Na by 2 plus under root Na by 2 whole square plus Ni square. Okay. And what will be the number of electrons? That would be Ni square by P. So these are the two formula, but along with that, two other formula will also come into action. What that would be? That would be usually number of acceptor atom will be much greater than Ni, right? So what will happen is that P will be approximately equals to Na only. So whatever the donor atom is there, sorry, whatever the acceptor atom is there. So what will acceptor atom do? It will give you a hole. So all the holes are taking electrons from the valence band, and if from the valence band electrons are going, that means it is creating some vacancy here. So all the electrons are going here. So what is the meaning is that every acceptor atom is giving you a hole. Okay. So P will be roughly equals to Na and N is roughly equals to Ni square by Na. So always for finding the minority charge carrier concentration, you will use the mass action law, not any equation. So you are remembering the formula only for the majority charge carrier concentration. That is for electrons it is Nd by 2 plus under root Nd by 2 whole square plus Ni square. For P-type semiconductor, for holes it is Na by 2 plus under root Na by 2 whole square plus Ni square. So these are the formula. Now we will write down the summary. So semiconductor, for intrinsic types of semiconductor, number of electrons is equals to number of holes is equals to Ni. For n type semiconductor, number of electrons are coming out to be Nd by 2 plus under root Nd by 2 whole square plus Ni square, and number of holes were coming out to be Ni square by n. And if Ni is much lesser than, or better I should write down, Nd is much greater than Ni, then n is approximately equals to Nd, and P is approximately equals to Ni square by Nd. Okay. What about the P type? In P type, Na by 2 plus under root Na by 2 whole square plus Ni square. Ni square by P. If Na is very much greater than Ni, then P will be approximately equals to Na, n will be approximately equals to Ni square by Na. There you go. Okay, well and good. So this is the summary of everything that we have studied. So don't feel like that, sir, there are a lot of formulas. There are not a lot of formula. Okay, let's solve the questions. So two questions are there, both you should be able to solve. Both of the questions you should be able to solve. At 300 Kelvin, n-type silicon semiconductor is doped with the donor concentration of Nd 10 to the power 16. Intrinsic carrier concentration is 1.5 into 10 to the power 10. Electric field is applied. Electron and hole mobilities are given. Equilibrium electron and hole concentration you need to find. So first thing I will see n-type semiconductor. What is the answer of first one? Answer of first one, n-type semiconductor. So for n-type semiconductor, I remember the formula n equals to Nd by 2. Although I will not apply this formula blindly in the examination. In the examination, what I will do is that, as of now we are learning it for the first time, that's why I am writing it. In the examination, what I will see is that Nd, which is 10 to the power 16, and Ni, which is 1.5 into 10 to the power 10. So this Nd is much greater than Ni, right? So n will be approximately equals to Nd only. So your electron concentration is coming out to be 10 to the power 16. And what about the hole concentration? So hole concentration will be Ni square by Nd. Again approximately, right? So what is Ni square? So intrinsic carrier concentration was 1.5 into 10 to the power 10. So what is the what is the square of 1.5? 2.25, right? So 2.25 into 10 to the power 20. You can do the square, right? 1.5 square would be 2.25, 10 to the power 10 square would be 10 to the power 20, divided by value of Nd, that is 10 to the power 16. Again here also there is a mistake, per centimeter cube. So number of holes would be coming out to be 2.25 into 10 to the power 4 per centimeter cube. So this is the answer of second one. Number of electron and number of holes we have told, right? Now what they are asking, total drift current density. Drift current density. So that will be because of the electrons, n q mu n into E. plus that will be because of holes as well. Now just think about it. Let's write down the formula. Okay, what is the value of n? Value of n is 10 to the power 16. And what is the value of p? 2.25 into 10 to the power 4. Q will be same for both of them. E will be same for both of them. What is mu and mu p? They are nearly double of each other. Like this is 650, this is 1350, nearly double of each other. But here what is the difference? 10 to the power 4, 10 to the power 16. Very large difference. 10 to the power 4, 10 to the power 16. Are you able to understand this point? Right? 10 to the power 4. That means 10,000. 10 to the power 16 is billions ahead. One guy is having 10,000 rupees, one guy is having billions of rupees. So, way more difference is there, no? Right? Even 10 to the power 2 and 1, you are getting 1 marks and one guy is getting 10 to the power 2 marks. Out of 100, one guy is getting 10 to the power 2 marks, one guy is getting 1 mark. So, this is way larger, right? So, this is 10 to the power 2 ahead, but this is 10 to the power 4, 10 to the power 16, 10 to the power 12 ahead. So, very large. Here the difference is only double. So, forget about this difference. Let's just understand that both are equal only. But this p is very smaller than n. So, you can see that n is very greater than p. So, approximately your j will be nearly equals to n q mu n into E only. So, here mu p is of no use and this also is of no use, although in the first question they are asking the concentration, but actually this is coming out to be of no use, right? So, in the previous lecture, whatever the theory that we have studied, now based on that theory we are solving all the numericals, nothing else, and some formula we have seen, nothing else, right? So, here because of this condition the formula has reduced. So, our hard work will be reduced now. Answer would be 10 to the power 16 into 1.6 into 10 to the power minus 19. Now you would see n is in the centimeter cube inverse, right? Q is in the coulomb. Mu n is only issue is centimeter. So I am just writing 1350. 1350. So here it is centimeter. It is in the centimeter square. And electric field is there in, where is the electric field? Volt per centimeter. Electric field is also there in volt per centimeter. Now you remember the unit of charge density. What is the unit? Charge density is I by A. So ampere by, what is the area? Meter square. But here everything we are dealing in centimeter. So what will be the unit? Ampere per centimeter square. Did you understand this point or not? Right? Rest all the things are fine. Volt, second, volt, centimeter cube, centimeter square. So our answer will also be ampere per centimeter square. Is that okay for you? Right? So what we can see, 13.5 10 to the power 2, 10 to the power 3, 10 to the power 13.5 into 1.6. 13.5 into 1.6. 21.6 ampere per centimeter square. 13.6 because 10 to the power 16, and here from here what I am doing, 10 to the power 2 I can take. So 10 to the power 18 it will become, I need to cancel 10 to the power minus 19. So 13.5 I can make here. So 13.5 into 1.6, that is coming out to be 21.6. 21.6. 21.6 ampere per centimeter square. This is the approximate answer. Now let's solve the question 2. This was your answer 1. Let's solve question 2. So now answer 2. At 300 Kelvin, n-type silicon semiconductor is having donor concentration of this much, intrinsic carrier concentration of this one. Find out the equilibrium, majority and minority carrier concentration. See the ND value and see the NI value. ND is much larger than NI? Absolutely not, right? So first thing is that I always need to see the type of semiconductor, N type semiconductor it is. Nd value is given as, so here very low doping they have done, 3 into 10 to the power 10 centimeter cube inverse, right? 3 into 10 to the power 10 centimeter cube inverse, and Ni is 1.5 into 10 to the power 10. Ni is 1.5 into 10 to the power 10 centimeter cube inverse. So now here a lot of people will do N equals to N nearly is equals to Nd, but now you are not going to do that because Nd and Ni are comparable. So value of N would be Nd by 2 plus under root Nd by 2 whole square plus Ni square. So Nd 3 into 10 to the power 10 divided by 2 plus under root 3 into 10 to the power 10. So it would also be 1.5 into 10 to the power 10 whole square. So yes or no? Did you understand what I did here? 3 into 10 to the power 10 divided by 2. So 1.5 into 10 to the power 10. This is what you will be getting here. No, 3 by 2. What that would be? 1.5. 1.5 into 10 to the power 10. And what is the value of Ni square? That will also be same. Basically, Ni is equals to Nd by 2. Ni here is equals to Nd by 2. Right? So from here you could directly see that I could have taken Nd by 2 under root 2. So Nd by 2 into 1 plus under root 2. That would be the answer. But yeah, let's solve in this manner. 1.5 into 10 to the power 10 whole square, right? So from here what I will be getting, this will be 1.5 into 10 to the power 10, and from here I can take 1.5 into 10 to the power 10 into under root 2, right? Because 1.5 into 10 to the power 10 whole square will come common, 1 plus 1 will be 2. Basically this is 1.5 into 10 to the power 10 whole square into 2. So whole square and under root will get cancelled out each other, under root 2 will remain there as it is, right? So what will be the answer you will be getting? Under root 2 plus 1, under root 2 plus 1 plus 1 into 1.5, 1.5. So 3.62, 3.62 into 10 to the power 10 centimeter cube inverse. This is the answer that you are getting. Okay, fine. Let's check the calculation again. Yeah, 3.62 into 10 to the power 10, right? So this is your electron concentration that I am writing down on the next page. 3.62 into 10 to the power 10 centimeter cube inverse. And what will be your whole concentration then? Because holes are the minority, right? So Ni square divided by N. What is the value of Ni square? Ni square is 2.25 into 10 to the power 20. Now what is the number of electrons? Number of electrons are 3.62 into 10 to the power 10. So if number of electrons you already know, and when it was intrinsic at that time what was the concentration, that also you already know. So you can surely find out the number of holes as well. So what will be the answer you will be getting? 2.25 divided by 3.62. 25 divided by 3.62. 0.62. 0.62, or you can write down 6.21. 6.21 into 10 to the power 9 centimeter cube inverse. This is the concentration of holes. Ten to the power 10 multiply, yeah. This is the concentration of electrons and this is the concentration of hole at the equilibrium. So you can see that concentration of electron is not much greater than the concentration of holes. And if you multiply both of them, if you multiply 3.62 with 6.21, you will get 2.25 roughly round. Sorry, 3.62, 3.62 multiply with 6.21 Yeah, so 22.5 we are getting. Because here 10 to the power 9 is there, no? So 2.25 into 10 to the power 20, roughly around that value only you are getting, right? Very easy thing. You should have solved it. You should have solved both of the questions on your own. You don't need to see the solution. Let's go to the next concept. Next concept is compensated. Okay, before that there is a question. After that there is compensated n-type semiconductor. So let's solve this question. Try doing it on your own. At 300 Kelvin, p-type silicon sample is having acceptor atom of 2 into 10 to the power 10. Okay, so previously it was intrinsic. Having 1.5 into 10 to the power 10, and then you did the doping of Na. That was 2 into 10 to the power 10. Now what is the line written? Only 60% of the acceptors are ionized. Only 60% of the acceptors are ionized. What does that mean? That means you wanted to get 2 into 10 to the power 10 holes. Every acceptor atom could have given you 10 to the power 2 into 10 to the power 10 holes. But actually you did not get that much of. Actually you did not get that much of holes. Why is that so? Because only 60% have been ionized. What does that mean? That your actual Na minus is 60% of Na. What does that actually mean? This was your acceptor, this was your valence band, and this was your acceptor energy level. So this was the conduction band, this was valence band, and this was the acceptor energy level. So let's just say there was 10 holes. Let's just say I did the doping of 10 acceptor atom only. Here it is given 2 into 10 to the power 10, but I am saying that I did the doping of 10 acceptor atoms. So 10 acceptor atoms will give me 10 holes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 holes. And here there are a lot of electrons. Bound electrons are there. A lot of bound electrons are there. Now what really happened was only 60% of them was ionized. That means from here only 1, 2, 3, 4, 5 and 6 electron games, and all these were ionized. So here only 6 holes you get. 1, 2, 3, 4, 5, 6. So in valence band you are actually getting only 6 holes. So here also the same thing is happening. 2 into 10 to the power 10 acceptor atoms you doped, but only 60% of the acceptor atoms are useful for you. This is what you can understand. So 60% of this, what that would be? 0.6 multiply with 2 into 10 to the power 10. I hope you know how to calculate the 60%. 60% of 100. I got 60% of marks. What does that mean? 60% of 100. So 0.6 into 100. That means I got 60 marks. So just I am multiplying with 0.6. So these are the actual number of holes. Like actual number of holes, this is not the number of holes now. This is not the equilibrium number of holes. Because of the boron atom, these many holes could have come. What is the equilibrium number of holes? That we will see. For that we need to apply the formula. And this is your p-type semiconductor. That's why my majority charge carrier concentration will be holes. So Na minus I have got, that is 1.2 into 10 to the power 10 centimeter cube inverse. Now number of holes will be, in place of Na, now I will be putting Na minus by 2 under root. So previously I was using 100% ionization. Here nothing about the ionization was mentioned. So 100% ionization in both of the cases. But here they have mentioned that 60% ionization is there. And this is comparable to Ni, right? This value. And what is the value of Ni? Ni value is 1.5 into 10 to the power 10 centimeter cube inverse. So these two values are comparable, right? So you solve this question, you write down the value of P, okay, because both of the values are comparable now. Actually you need to calculate total current density. So you know that if I apply the formula of total current density, what that would be? In the total current density, number of electrons will also come into action, number of holes will also come into action. So NQ mu N plus electric field, sorry, multiply with electric field, and PQ mu P multiply with electric field. Then you saw that number of holes that you will get, and number of electrons that you are going to get, they will be nearly equal, because Na is nearly equals to Ni. So you cannot ignore anything. Both of the parts will come into action. This part will also come into action and this part will also come into action. So that's why you are doing all the calculation. Do this calculation. I will take some break because of the cough that I am having. So I need to take some break and then I will come back and we will solve this particular question. Yeah, welcome back. So when I put the values, the answer I am getting is 2.21 into 10 to the power 10 centimeter cube inverse. Okay, so this is the number of holes. So again I am writing number of holes are 2.21 into 10 to the power 10 whole cube inverse. So what will be the number of electrons? That would be Ni square by P. So that value I can put. What is the value of Ni square? 2.25 into 10 to the power 20 divided by value of P is 2.21 into 10 to the power 10. So this answer I am getting is 1.01 into 10 to the power 10 centimeter cube inverse. But our target was to find out the drift current, that was NQ mu n into E plus PQ mu P into E. Here what I can take common? I can take Q into E, I can take common, right? Q into E. So number of electron concentration will be multiplied with mobility. Number of hole concentration will be multiplied with mobility. 1.6 into 10 to the power minus 19. Value of electric field is 10. Electron concentration is 2.21 into, electron concentration is 1.01. Electron concentration is 1.01 into 10 to the power 10 and mu n value is 1350 plus here this is 2.21 into 10 to the power 10 and mu p value is 650. So there you go, this is what we need to solve. So everything is going into centimeter, like volt per centimeter, centimeter cube. So answer will be ampere per centimeter square, right? That would be the answer. Now from here I can take out 10 to the power 10 outside, right? So this will be 10 to the power 11. So 1.6 into 10 to the power minus 7. So this is 10 to the power minus 18 already, and 10 to the power 10 is coming outside. So 10 to the power minus 8, right? 10 to the power 10 is coming outside. So 10 to the power minus 8. Here what I am getting, 1.01 into 1350. 1.01 into 1350 plus 2.21 into 650. So 2800 I am getting. 2800. This is what I am getting. Okay. Then 2800 into 1.6. I am getting 4480. 4480 into 10 to the power minus 8 ampere per centimeter square. And if I want to write it down in a better manner, what that would be? 44.8, because 10 to the power 2 I want to give this to this one. So 10 to the power 2 into 10 to the power minus 8, what that would be? 10 to the power minus 6. So that would be micro ampere per centimeter square. So that would be the conduction, that would be your drift current density, 44.8 microampere per centimeter square. Okay, so that would be this would be the answer. Very simple thing. Just here the new thing was that 60% of Na. Then from there you find out the value of Na. From there you find out the value of hole concentration. From there you got the value of electron concentration. Then you applied the formula and you solved it. Now there is something called compensated N type of semiconductor. So this is an N type of semiconductor, but here donor atom and acceptor atom both will be doped. What I mean to say is that previously you were having intrinsic, right? Previously it was intrinsic, but here you will be doing the doping of Na as well, you will be doing the doping of Nd as well. But since this is N type, that means Nd will be larger than Na. Are you able to understand this point? So here what will be your mass action law? Mass action law will be N into P is equals to Ni square. Because previously it was having Ni when it was intrinsic. Now the electron concentration is N, hole concentration is P, right? So N into P is equals to Ni square. This is your mass action law. What will be your charge neutrality equation? Did you understand this point? Compensated N-type semiconductor, since it is N-type, Nd will be greater than Na, but both of the donor atom and acceptor atom both will be doped. Okay. What will be your neutrality equation? Negative charge is Na, right? Negative charge is Na and electrons, and positive charge is Nd and holes, right? Who is the majority here? Who is the majority? Majority is N, and who is the minority? Minority carrier concentration is P. So whom I will replace? I will replace P here, right? So value of P will come out to be Na minus Nd plus N, right? Or what you can write down? Okay, it is fine. Previously what was the scenario? When we solved this particular question, when we solved this particular equation. So here the scenario was N minus Nd, right? So what I will write down? Can I write it down in this manner? N minus Nd minus Na. This is the value of P. This is equation 1. This is equation 2. So previously what did you solve? N into P is equals to Ni square and P is equals to N minus Nd. This is what you solved. Previously this is what you solved. And you know the answer. What was the answer? N is equals to Nd by 2. Now in place of Nd, what you have replaced? Nd minus Na. In place of Nd, what you have replaced? Nd minus Na. Because this is N minus Nd minus Na. So in place of Nd, what you are getting? Nd minus Na. So what do you think? What will be the answer? You can solve it on your own. So the electron concentration will come out to be Nd minus Na by 2 plus under root Nd minus Na by 2 whole square plus Ni square. There you go. So what you will see first? First, in these kind of questions, you will see that which is greater, Nd is greater or Na is greater. From that, you will decide that who is the majority, who is the minority. From there, you can write down this formula very directly. Because you know that Nd is greater than Na. So here you will write down something positive, no? So Nd minus Nd divided by 2 plus under root Nd minus Nd whole square plus Ni square. Right? So in place of Nd, you are just putting Nd minus Na. And what will be your whole concentration? So for that, Ni square by N. And if your Nd minus Na is much greater than Ni, okay, that means doping is very high. Both of the dopings are very high, or Nd is very high. Whatever it is, Nd minus Na is very greater than Ni. Then what will be the answer? N will be approximately equals to Na minus Nd, right? Because you can see that Nd minus Na, not Na minus Nd, because Nd is higher, no? It would be approximately equals to Nd minus Na. And what about the holes? That would be Ni square by Nd minus Na. There you go. Similarly, there will be compensated p-type semiconductor as well. I don't think it is tough to remember. Very easy. Compensated n-type, compensated p-type. That means both donor and acceptor atoms are there. Since it is n-type, donor atom is more. So directly I can write down the formula. Nd minus Na divided by 2 plus under root Nd minus Na divided by 2 whole square plus Ni square. There you go. What about this one? compensated p type. So what do you think, what will be equilibrium hole concentration? That would be Na minus Nd divided by 2 plus under root Na minus Nd divided by 2 whole square plus Ni square. And what will be your electron concentration? That would be Ni square by P. And if your Na minus Nd is much greater than Ni, then your P will be Na minus Nd, and your approximately your P will be approximately Na minus Nd, your N will be approximately Ni square upon Na minus Nd. There you go. Okay, so not tough to remember, everything is easy, not tough to remember at all, because you know that Na is already greater than Nd because it is compensated p type. So this is the question. Like this question will just clear everything that we have studied till now. We have been studying semiconductor physics for roughly around 6 hours now, 4 hours in the previous video, 2 hours in this video. So in this 6 hours, whatever that you have studied, most of the part would be covered in this particular question. So what you need to find, calculate the electron and hole concentration and the current density. Okay, so I would require what it is given, compensated p type, it is already given, or without, even if it was not given, then you could see that this is the value of Na, this is the value of Nd. That means both of the dopings are there. Na is there 10 to the power 14 per centimeter cube, and Nd is there 2 into 10 to the power 13 per centimeter cube. So you can directly see that Na is greater than Nd. If Na is greater than Nd, that means it is p type, compensated p type, right? And what is the value of Nd minus Na? Sorry, Na minus Nd, because it is p type, so I will calculate Na minus Nd. So this is your Na is actually 10 into 10 to the power 13, right? So 10 into 10 to the power 13 is subtracted from 10 into 10 to the power 13. 2 into 10 to the power 13 is subtracted. So what will be the answer? 10 minus 2 will be 8. I hope you are able to do this calculation. This is not tough. Na minus Nd. Na minus Nd. 10 into 10 to the power 13 minus 2 into 10 to the power 13. So 8 into 10 to the power 13 centimeter cube inverse. And what is the value of Ni? Ni is 5 into 10 to the power 13 centimeter cube inverse. So again the values are comparable, right? What all things are given? Intrinsic carrier concentration, all these things are given. Electric field is given. So first let's find out the electron and hole concentration. So for finding out electron and hole concentration, this is something I require and this is something I require. My job is done. So I can find out the hole concentration by my formula Na minus Nd by 2 plus under root Na minus Nd by 2 whole square plus Ni square. What is the value of Na minus Nd? Na minus Nd is 8. 8 divided by 2 will be 4. So 4 into 10 to the power 13 plus under root. Now what will be 4 square? That would be 16. 10 to the power 13 will be 10 to the power 26 plus Ni square. 25 into 5 square will be 25, or this will be 10 to the power 26. So here 10 to the power 13 will come outside and 4 will be there. So 4 plus 25 plus 16, what that would be? 41 into 10 to the power 13. Did you understand this point? 10 to the power 26 will be coming common. So 10 to the power 13, 25 plus 16, that would be 41. So under root 41 plus 4. So 10.4, 10.40 you are getting. So 10.4 into 10 to the power 13 centimeter cube inverse. So the number of holes are coming out to be 1.04 into 10 to the power 14. Roughly I can call it in this manner, right? Yeah. And answer also matching. Yeah, 1.04 into 10 to the power 14. And number of electrons will come out to be Ni square by P. So 25 into 10 to the power 26 divided by 1.04 into 10 to the power 14. Reciprocal into 25. So 2.4 into 10 to the power 13, right? 2. So basically here I am getting 24. 25 divided by 1.04 is 24 I am getting, and 24 into 10 to the power 12 I will get. So if I need to make 10 to the power 13, so what I will do? 2.40 into 10 to the power 13 centimeter cube inverse. This is my number of electrons. Now what I need to find? I need to find the current densities. What I need to find? I need to find current density. I know that number of electrons and number of holes both will be drifting in the same direction, so both of the currents will be added. So N Q mu n into E plus P Q mu P into E. This value I am having, P value I am having, Q value I already know, E value also I am having, right? E value is given. The only concern is mu n and mu P. They haven't given the value, but they have given mu P divided by mu n is 1 by 2. Mu P divided by mu n is 1 by 2. This is what they have given. So I can write down 2 mu P is equals to mu n. So mu n is just that double of mu P, right? This is what they have given. Now I need to apply this formula. But before that, there is one more thing given. Intrinsic resistivity they have given. So somehow I will use this particular thing. So resistivity, intrinsic resistivity they have given, that is 50 ohm into centimeter. Okay, centimeter. 50 ohm into centimeter. So everything is going into centimeter only, right? And that would be equals to, this is intrinsic. So here what I will write down? Intrinsic conductivity, that is Niq into mu n plus mu p. Did you understand this point or not? Right? This is the intrinsic resistivity. So intrinsic resistivity would be equals to 1 by intrinsic conductivity. What is intrinsic conductivity? Nq mu n plus Nq mu p. Sorry, Nq mu n plus Pq mu p. N equals to P equals to Ni. So Ni into Q bracket mu n plus mu p. Right? One thing I know that mu n is equals to 2 mu p. So here what I will get? 1 by Ni Q into 3 mu p. So value of mu p will be 1 by 3 into Ni. What is the value of Ni? I again forgot the value of Ni. Ni was given as 5 into 10 to the power 13. So let's write down in a better manner. 5 into 10 to the power 13. So 1 by 3 is already there. 5 into 10 to the power 13 into charge 1.6 into 10 to the power minus 19 into 50. So answer will be coming in centimeter square. Centimeter square upon volt into second, because everything is going into centimeter. So how will I solve it? 1.6 15 into 1.6 into 50. This I have done, this I have done, this I have done, this I have done. And what this will give you? 10 to the power minus 6. So if it goes upward, it will give you 10 to the power 6. 10 to the power 6 divided by 1200. If I take the reciprocal, I am getting 8.33 into 10 to the power minus 4. So answer would be 8.33 into 10 to the power minus 2. Something doesn't seem like 10 to the power minus 2, this much low conductivity, this much low mobility, 8.33 into 10 to the power minus 2. Oh, sorry, 10 to the power plus 2, sorry, 10 to the power plus 2, because this is 10 to the power 13 and 10 to the power minus 19. Because I know that generally what value we are seeing, 1350 and 500, this is the general value of mu p and this is the general value of mu n. Basically, I know that in centimeter square into volt into second. So here I was messing up the calculation, I was getting this thing. So just I thought that this much low value of mobility cannot be there. So then I know that, yeah, 8.33 into 10 to the power minus 4 you are getting, and here you are getting 10 to the power plus 6. So this will be 10 to the power 2. Okay, yeah, centimeter square volt into second. So from here mu n value you would know just the double of it, and that would be 16 point. I should not have used the calculator for this, double of it, I should have done it, right? But yeah, now it's been roughly around 4 to 5 hours since I am recording, so I'm training as of now. So after this question I will stop, I will come back tomorrow. But videos I will add up together, but after this question I will have to stop because I'm not at my 100% now, right? So yeah, mu and mu p value we are having, so now we can apply the formula. One thing I can see that q into E I can take common. So n into mu n plus p into mu p. So 1.6 into 10 to the power minus 19. What is the value of E? Value of E is 3. What is the value of n? N is 2.4 into 10 to the power 13 into what is the value of mu n? That is 16.66 into 10 to the power 2 plus what is the value of P? Value of P is 1.04 into 10 to the power 14 and 8.33 into 10 to the power 2. So here 10 to the power 15 I am getting, 10 to the power 16 I am getting. So let's make it 10 to the power 16 only. So if I take out 10 to the power 16, so 4.8 into 10 to the power 16 I am taking out, 10 to the power minus 3 I will get. And inside 0.24 into 16.66, 0.24 into 16.66 plus. I hope you are understanding how I am doing the calculation. Here 10 to the power 13, 10 to the power 2, 10 to the power 15 it would be, and here 10 to the power 16. So here also I thought of making 10 to the power 16. So for that what I need to do, 2.4 can be replaced with 0.24. So 10 to the power 16 I am taking outward. So 10 to the power minus 19 into 10 to the power 16, that would be 10 to the power minus 3. 1.6 into 3, that I know, 48, 4.8. And inside I am doing the calculation, 2.4 into 0.24 into 16.66. So that value I am getting, and then 1.04 into 8.33. So 12.66 you are getting, 12.66 here, and that will be multiplied with 4.8. So 16.77. Yeah, 16.77. So we are getting 60.77. 10 to the power 3 can be 10 to the power minus 3 can be replaced with milliampere divided by, everything is going in centimeter, right? So centimeter square. So that would be the answer. Again, not very tough question, but calculation is there. So you need to have some patience and solve the question in this manner. Calculations are there, but again, easy question only, right? So acceptor atom was also there, donor atom was also there. Then you subtracted both of them. You got to know that it is comparable to Ni. So you have to apply the exact formula. From there, you find out the value of concentration of electron and holes. Then you got to know that I need the mobility value as well, but only relation is given. Then you search for some other value. So this other value was given, which was 50. From here you could get to know that yes, now I can apply another formula and I can get my answer, right? So from there you got the value of mobility, and that mobility value you used there, and you got the conduction current, sorry, you got the drift current density. Okay, that is the answer. So for this video, this part is completed, but another part is there. In this part, what we discussed some terms, some formula, and then we solved some question. So within 10 to 15 minutes, you will be able to revise it. So just go back, collision time, effective mass, then mobility, E tau by m. That formula came into action, E tau by m star. Then drift velocity, Vd is equals to mu e. Then conductivity, n q mu, where n is the charge carrier concentration, q is charge only, and mu is the mobility. And then charge density, J is equals to sigma e. Sigma value you already know, and E value you will be given, right? From there you can find out the current as well, because current is simply equals to J into A. For intrinsic carrier concentration, n is equals to P is equals to Ni, so you can put there and you will get your answer. For n type semiconductor, n is much greater than Nd. Sorry, for n type semiconductor, n is much greater than P, and for p type semiconductor, P is much greater than n. Then we studied about mass action law, n equals to n into P is equals to Ni square. So always at the thermal equilibrium, number of electron concentration multiplied with the whole concentration will be equals to a constant, that is equals to Ni square. Okay, then charge neutrality equation, who is the positive charge? Positive charge is Nd plus P, that would be equals to Na plus N. From these two equations, we got to know that we can find out the concentration of electron and holes in semiconductors. For intrinsic semiconductor, n equals to P equals to Ni. For n type semiconductor, n is equals to, because for the majority charge carrier concentration, we remember the formula. For minority, we will apply again the mass action law only. So for majority, the answer is coming out to be, for n type semiconductor, for majority, the answer came out to be Nd by 2 plus under root Nd by 2 whole square plus Ni square. That is the concentration of electrons. Then concentration of hole is Ni square by n. For the p type semiconductor, concentration of holes is Na by 2 plus under root Na by 2 whole square plus Ni square. And concentration of electron from the mass action law you can find out. Then we studied about compensated n type semiconductor and compensated p type semiconductor. In compensated semiconductors, both of the dopings would be there, but for n type semiconductor, Na is greater than Nd. For p type semiconductor, sorry, for n type semiconductor, Nd is greater than Na. For p type semiconductor, Na is greater than Nd. For both of them, you can write down the formula of electron concentration and hole concentration, just by the formula that you have already remembered. In place of Nd, you will place Nd minus Na, and in place of Na, you will place Na minus Nd. For both of them, you will remember the formula for majority charge carrier concentration. For minority, you will just apply the mass action law. There you go. This is how you can devise this particular lecture. In this lecture only, we will study about some graphs. Okay. So we have studied about mobility, but how this mobility will change with respect to the temperature. We have studied about conductivity, how this conductivity will change with respect to the temperature. We have studied about drift velocity, right? So how drift velocity is related to electric field. So these kind of a lot of graph would be there. For all the parameters that we have studied, we will see the graphs and we will see how those graphs will go. Okay, so that we will study in this video only, but in the second half. Okay then, yeah, thank you very much. Happy learning. Hi everyone, welcome back. Welcome to the second part of this video. In this part, we are going to plot some graph. We will plot the graph with respect to temperature, with respect to doping concentration, and all these kind of things. So what all parameters we have seen? So first parameter we saw, that was carrier concentration, right? Intrinsic carrier concentration. Then we saw about mobility. Then we saw conductivity. Then current density, current, all these parameters we saw. So we just need to plot the graph with respect to temperature. Then some other graphs also we will draw. So you need to have patience in this part of the video. Okay, just keep on looking whatever that I am telling. Now you let me know one thing. What we are doing firstly, we are taking an intrinsic semiconductor and we are plotting intrinsic carrier concentration versus the temperature. Intrinsic carrier concentration versus the temperature. But it will have an effect on Eg as well and temperature as well. So first let's understand by our simple concept. What was our concept? At 0 Kelvin, what was the condition? This was your valence band, this was your conduction band. I am talking about intrinsic semiconductor. That means I am talking about pure silicon. So valence band was filled with electrons and conduction band was empty. As the temperature increases, at 300 Kelvin, what really happened? Some electrons from here went to conduction band. Some electrons from here went to conduction band. So in conduction band, there were some free electrons and here there were some holes. these electrons and these holes were known as intrinsic carrier concentration. At the beginning, at 0 Kelvin, there were electrons, but these electrons were bound electrons. So you were not calling it intrinsic carrier concentration. No, these were the intrinsic carrier concentration. These two electrons and these two holes are known as intrinsic carrier concentration. They are not a carrier concentration, right? Because they are bound. Since they have become free now, since they have a vacancy here, they are known as intrinsic carrier concentration. So as the temperature increases, here how much intrinsic carrier concentration was there? 0. But as the temperature increases, you are having 2 electrons and 2 holes, and that is known as intrinsic carrier concentration. So as the temperature was increasing, what was happening? The covalent bond was breaking up, and because of that you are getting free electrons and holes. So intrinsic carrier concentration increases with increase in temperature. So what will happen? At 0 Kelvin it was 0 only, then slowly it will keep on increasing. So the graph will, just a second, the nature of a graph will go somewhat like this, like it will keep on increasing. Okay, just like you can never make the perfect graph that sir this is how it will go for all the semiconductor. For some semiconductor it can be different, for some semiconductor it could be different, but one thing I surely know that it will be just keep on increasing. It will have increasing nature. Now how it will be increasing, sir? In this manner it is increasing, but just only one thing I know, that it will have increasing nature, that carrier concentration will never decrease with respect to the temperature. Okay, so in the examination if these kind of graphs are given in the options, so only thing you need to notice is that whether it is having increasing nature or not. So whichever the graph is having increasing nature, that would be your answer. That's it. Okay, but now this graph we have drawn, but there is an expression. There is an expression which will relate your intrinsic carrier concentration, temperature and Eg value. What is Eg? Eg is band gap. So there is a particular expression which will relate intrinsic carrier concentration, temperature and band gap. What is that expression? So that expression formula I am going to write down. Sir, how that formula came? That derivation we will see later on. In this chapter only we will see the derivation later on, but as of now you need to remember this particular expression. So your Ni square is given as some constant A naught T to the power 3 e to the power minus Eg by Kt, where A naught is a material constant. It will depend on the material. It is a constant value. T is the temperature in Kelvin. Eg is the band gap at a particular temperature. Eg is the band gap at a particular temperature. K is the Boltzmann constant and T is the temperature again. What is the value of Kt at room temperature? What this Kt is known as? Thermal energy. So what is the value of Kt at room temperature? Do you remember the value? If you don't remember, then it is not good. I told you to remember. What is the value? Although in examination there is very high chance that this value will be given, but still at least at the room temperature you need to remember it. 0.0259 electron volt, right? Say yes or no. Okay, or it can be written as 25.9 milli electron volt, or it could be written at 26 milli electron volt as well. So at least remember this value, 26 milli electron volt. Yeah, so don't write down anything, like everything is already written. I will just remove this slide and then I will show you that everything is already written. Now this is the expression between Ni square, temperature and Eg. How this formula came, that derivation we will see later on, but as of now you remember it. From here, how can you find out the value of Ni? So this power can go here. So A naught to the power 1 by 2. What it will become? A naught to the power 1 by 2. This will also be a constant only. So can I write down as B naught? Can I write it down as a B naught? Basically whatever the constant was there, this constant is different, but again it is a constant only, right? T to the power 3 by 2 e to the power minus Eg by 2 Kt. So either you remember this expression or you remember this expression. Any of the expression you can remember. Secondly, this is the Eg at a particular temperature. This is the band gap at a particular temperature. What is the relation between band gap and the temperature? So band gap reduces with increase in the temperature. Do you remember that? Band gap will reduce with increase in the temperature. So Eg was given as Eg naught minus beta naught T, where Eg naught is the temperature, Eg naught is the band gap at 0 Kelvin. So as the temperature increases, this value will decrease. So now in place of Eg, if I replace this Eg naught minus beta naught T, what I will be getting? Minus Eg naught plus beta naught T. Why plus beta naught T? Because there is a negative sign, divided by 2 Kt. Now e to the power minus Eg naught divided by 2 Kt, e to the power minus, plus sign is there, e to the power beta naught t divided by 2kt. So t and t get cancelled out. So what you are getting, e to the power beta naught divided by 2k. I am only looking at this expression, e to the power beta naught divided by 2k. Is this a constant? K is a Boltzmann constant, beta naught was a constant value only, 2 is also a constant. So this is also constant only. So this particular part is constant only. B naught is a constant, multiply with the constant, it will be a constant only. Are you able to understand this point, what I am saying? So what you got to know here is that B naught multiply with the constant, what that would be, some new constant C naught, t to the power 3 by 2 e to the power. Now in place of Eg what I can replace, Eg naught by 2kt. So in place of Eg what I can replace, Eg naught. So e to the power minus Eg naught by 2kt. So either here you can write down Eg or you can write down Eg naught as well. Anything you can write down, because you know that there is a linear relation between Eg and the temperature. As the temperature increases, Eg goes down. So in some textbook you will find out that a particular band gap at a particular temperature is written, and in some textbook you will see that band gap at 0 Kelvin is written. Okay. So band gap at 0 Kelvin they can write down, band gap at a particular temperature also they can write down anything. So don't get confused. Okay. Particularly we will write down the band gap at a 0 Kelvin. So what I will write down, some constant t to the power 3 by 2 e to the power minus Eg naught divided by 2kt. So this is the relation, this relation you need to remember. So I will just remove everything that I have written and then I will show you what has been written under the slide. So this is written. The intrinsic carrier concentration Ni of a semiconductor depends on the band gap and the temperature in this manner. Ni square equals to a naught t to the power 3 e to the power minus Eg naught by kt. From here if I want to find out the value of Ni, that would be a naught to the power 1 by 2, so that will be some constant b naught t to the power 3 by 2 e to the power minus Eg naught divided by 2kt, right, where Ni is the intrinsic carrier concentration, a naught is material constant, T is the absolute temperature, Eg naught is the band gap at 0 Kelvin and K is the Boltzmann constant. You don't need to remember the value of Boltzmann constant, you just need to remember what is the value of Kt at 300 Kelvin. The value of Kt at 300 Kelvin is 26 milli electron volt. Well and good. Okay. And now in this expression if you see, if temperature increases then what will happen? This value will increase. What I am saying, again let me write down here. Some constant, again I am writing down some constant as a naught only. Whatever the constant is there, don't look at this constant. Only matter of concern is t to the power 3 by 2 e to the power minus Eg naught divided by 2kt. So if temperature increases, then this value will increase. This value will also increase. 2kt will also increase. If 2kt is increasing, that means this particular value is decreasing. If 2kt is increasing, that means this particular value is increasing. So on e to the power minus x, so this x is decreasing. X is decreasing. What does that mean? Then this value will increase. What do you know? E to the power x. If x increases, then e to the power x increases. You know that, right? What about e to the power minus x? What is e to the power minus x? E to the power minus x is 1 upon e to the power x. So if x increases, then this whole value will increase. 1 upon something is increasing, that means this value will decrease. Right? But what is happening here? In our case, what is happening? X is actually decreasing. Eg naught divided by 2kt. If temperature increases, this whole value decreases. So x is actually decreasing. If x is decreasing, that means this value is decreasing. If this value is decreasing, that means this whole value is increasing. So e to the power minus x is actually increasing. So this part is also increasing, this part is also increasing. So the whole part will increase only. Are you able to understand this point or not? Very, very simple thing. Right? Just mathematics. If temperature increases, this part increases. If temperature increases, then this whole part also increases. Because here, if temperature increases and this part increases, this whole part decreases. If this whole part is decreasing, that means e to the power minus x is increasing. So if temperature is increasing, then Ni is also increasing. So from the formula also you can prove it. Right? So if temperature increases, Ni increases. So if temperature increases, Ni increases. If Eg increases, then what will happen to Ni? Do it on your own. This is simple mathematics, you should be able to tell it. If Eg increases, what is the formula? Some constant t to the power 3 by 2 e to the power minus Eg by 2kt. So forget about the temperature. Who is increasing now? Eg is increasing. So if this value increases, Eg value increases, then what will happen? E to the power minus x will increase. If e to the power minus x is increasing, that means this whole value will, sorry. If Eg is increasing, that means this x is increasing. So if x increases, then e to the power minus x decreases. If Eg is increasing, that means this whole value is increasing. That means e to the power minus this whole value will decrease. That means if Eg increases, then Ni will decrease. And it is pretty obvious as well. Why it is obvious? Because if the gap between conduction band and valence band increases, if this gap increases, then this electron will require more energy. This electron will require more energy to go here. So let's just say at room temperature it was going here. So at room temperature you were getting one electron and one hole. But if Eg gap is very large, then it may happen that this electron is not able to cross this much of energy. So you will not get any electron. Are you able to understand this point? So if Eg is very large, then you will not get free electrons and holes. So to get the free electron and holes, Eg should be low. So if you are increasing the Eg, that means intrinsic carrier concentration will decrease. Very simple point. Within 10 seconds you should be able to revise it. Only formula you need to remember is Ni equals to A naught T to the power 3 by 2 e to the power minus Eg naught divided by 2 kT. If temperature increases, Ni increases. By the concept as well you can understand, by the formula as well you can understand. Because temperature increasing, T to the power 3 by 2 increases. Temperature increases, then Eg naught by 2 kT decreases, e to the power minus, if x is decreasing, that means e to the power minus x is increasing. So increasing, Ni will increase only. By the concept also you can understand, at higher temperature more covalent bond will be broken. If more covalent bonds are broken, that means more electrons will be there, more holes will be there. That means carrier concentration will increase. Now if Eg increases, that means the gap between conduction band and valence band will increase. So at lower temperature it might happen that electron is not getting enough energy to go from valence band to conduction band. That means the carrier concentration will decrease. That's it. Or from the formula as well you can see it. Very simple. Within 10 seconds you will be able to revise it, and this is the graph which can be coming in your examination. So this was about our intrinsic carrier concentration. Let's go to our electron concentration in n-type semiconductor. So previously we were studying about intrinsic semiconductor. Now we will study about n-type semiconductor. In n-type semiconductor we will be particularly looking at electron concentration. Okay, so look at the screen very carefully. At 0 Kelvin what was happening? Because of the pentavalent atoms, because of the impurity, just below the conduction band you are having a donor energy level. But at 0 Kelvin none of the electron is having any energy to go from donor level to conduction band or to go from valence band to conduction band. So no electrons are there in the conduction band. What does that mean? That charge carriers are, number of electrons are 0. When I say electron, that means I am talking about free electron. And what do you mean by free electron? Free electron means electrons in the conduction band, right? At least 20 times I have repeated this line. Electron means free electron. Free electron means electron in the conduction band. So at 0 Kelvin there is no electron in the conduction band. Just as the temperature increases. So just as the temperature increases, what will happen? From here electron will start going. Along with that, some covalent bond will also be broken. So slowly, yes, the number of electrons are increasing here. But at mid temperature what will happen? All these will be completely ionized because this gap is very low. So they will be completely reaching here. They will be completely reaching here. From here hardly, previously 2 electrons were coming, so now here 3 electrons would be coming. So let's draw the graph from 0 Kelvin till mid temperature. So what was happening? At 0 Kelvin there was nothing. At 0 Kelvin there was 0 electrons. But slowly the electrons started increasing. At one particular point it will become constant. At the mid temperature it will become constant. Why is that so? Because all these have been already ionized. At the mid temperature what happens is that whatever the Nd we doped, because of one Nd we were getting one electron. So all the electrons are ionized. That means all the electrons have reached to the conduction band. Now hardly some 2 or 3 electrons are coming from the valence band. So almost it has become constant, or you can say that it will rise slowly. Here it is rising fastly. Why is that so? Initially why it is rising fastly? because these are being ionized. Nd is a lot more than the intrinsic carrier concentration. I hope you remember that Nd will be much more than the intrinsic carrier concentration. Let's just say intrinsic carrier concentration was 10. So Nd would be somewhere around 100. So those hundreds have already reached here. Now out of these 10, let's just say 9 have already reached. So 9 plus 1, 10 will come. With the increase in temperature, only a few electrons will be coming from the valence band, because till the mid temperature all these have been already ionized. Are you able to understand this point? At low temperature only they will get enough energy to get ionized. So till the mid temperature all these are already ionized. If you are increasing the temperature, what will happen? Some of these will also come here, but in a very few amount, because donor atoms are already very much higher. So these donor electrons are already very much higher. So almost it will become constant. At the mid temperature, almost it will become constant. But now what you are doing, you will keep on increasing the temperature. What you are doing, you will keep on increasing the temperature. So these are already there. These have already reached here. These electrons have already reached here. But now what will happen is that because the temperature is very high, so all of these covalent bonds will start breaking up. So a lot of covalent bond will start breaking up. So a lot of covalent bonds are breaking up. So from valence band as well, a lot of electrons are coming now. So now what will happen is that the number of electrons will increase drastically after a particular temperature, at a very high temperature. So a very interesting graph. Usually people don't understand this graph, they don't know what is actually happening, but I have given you the whole condition that what is actually happening. At 0 Kelvin, no electron is reaching, no charge carrier. At low temperature, these guys have got enough energy, so they are increasing. So here number of electrons are increasing. From the valence band as well, some electrons are coming, but at the mid level temperature, when you have reached already here, when you have reached already at temperature T1, at this T1 temperature, all of these electrons have been already ionized. Only a few electrons are coming, which are hardly increasing any number of electrons, right? So number of electrons are almost constant. But if you keep on increasing the temperature, at very high temperature, what will happen is that a lot of covalent bonds will break and a lot of electrons will come into the conduction band. Okay, so this region, this particular region will be known as which region? Ionization region. Ionization region. Why ionization region? Because in this particular region ionization is happening. These electrons from the donor level is going into the conduction band, and this is known as extrinsic region. This is known as extrinsic region. Why extrinsic region? Because in this region already all of these electrons have been ionized. In this particular region, all of your donor energy level electrons have been ionized, or whatever the electrons that are coming from the donor atom, all these electrons are ionized in this region. So that's why it is known as extrinsic region. Basically you wanted your electron region to be this, right? You wanted the number of electrons to be this only. But when you kept on increasing the temperature, at very high temperature, what really happened? That a lot of electrons are coming from the valence band as well. What does that mean? If a lot of electrons are coming from the valence band, so this kind of mechanism was happening in which kind of semiconductor? In the intrinsic semiconductor, no. Initially you were having intrinsic semiconductor. You know that Ni value was very low. So for that what you did? You did the doping of donor atoms. Because of the donor atoms, you got some electrons, right? But if you kept on increasing the temperature, how you were getting this Ni? This Ni you were getting because from here some electrons were going, right? And why these electrons were going? Because of the temperature only. And if you have increased the temperature very high, that means all of them got thermal energy. So a lot of electrons have got the thermal energy. So these electrons are excited because of the thermal energy, not because of the donor level, not because from here. These electrons are coming from here, and if the electrons are coming from the valence band, what does that mean? That means they are coming because of the thermal energy. And this thermal energy phenomena happens majorly in which kind of semiconductor? Intrinsic semiconductor. So this particular region is known as intrinsic region. So what did you understand here? At very high temperature, at very high temperature, the extrinsic semiconductor will start behaving as intrinsic semiconductor. That's why you do not operate your semiconductor at a very high temperature. You will operate your semiconductor in this particular region. This is your working region. A very important graph, and I am expecting this graph to be coming very soon in your examination, very soon. Okay, so this is your electron concentration with respect to temperature, and this particular point is known as freeze out point, because here there are no free electrons. So this particular point, or sometimes in some textbook as well, you will see that this region is known as freeze out region. So you can call it freeze out region or freeze out point, whatever you want to call it, but important parts are these two regions, extrinsic region and intrinsic region. So at a very high temperature, what will happen is that a lot of valence band electrons will get thermal energy, or you can call it a lot of covalent bond electrons will get enough thermal energy, and they will create electron hole pairs, and this phenomena happens in intrinsic semiconductor. So your semiconductor, your n-type semiconductor is working as an intrinsic semiconductor only. So you don't operate your semiconductor at a very high temperature. Now you would say that sir, at very high temperature, sir, we are getting a lot of electrons, so it is good. The device may burn out. Okay, what you will say that, sir, I will operate my semiconductor at a very high temperature. So do you operate your mobile when it is very heated? No, you operate the mobile at the working condition, no, at the temperature, at the room's temperature only, no. Like if your mobile is very heated, then you will be tensed, right? Because your device may burn out. The chips inside your device, the chips inside your mobile may burn out, and your mobile may start and your mobile may stop working, right? So that's why you do not operate any semiconductor at a very high temperature. Although the number of electrons are very high, but the device will be burning out, and actually there has been no use of these donor atoms. Since a lot of electrons are coming from here, the donor atom will become minority only. I should not say minority, that means what I mean to say is that these numbers, let's just say these numbers Nd was 100, but at very high temperature what will happen is that these electrons will be very large. These electrons will be roughly around 1000. So this 100 will not look anything around these 1000. So there was no use of this doping. Even if you haven't done the doping, still it would be the same only. Are you able to understand this point? Even if you did not do the doping, then also these 100 will not make any sense. This will become 10,000, 1 lakh. So in 1 lakh, if you add 100, what does that mean? Nothing, right? So almost it is working as an intrinsic semiconductor only. Are you able to understand this point? Right? So at very high temperature, we will never operate our devices, because device will be burning out. Now what may happen is that in the examination, although this graph we have plotted n versus t, but in the examination they can ask you the graph n versus 1 by t. I don't know why. Basically a lot of curves in our industry as well, when you go into the industry, you will draw a lot of curves with respect to 1 by t, not with respect to t, with respect to 1 by t. So n versus t graph is given. Can you draw the graph of n versus 1 by t? Simple mathematics, you should be able to do it on your own. Here 1 by t value is low. This is the axis of 1 by t, right? So here 1 by t value is low. What does that mean? That t value is very high. So at very high value, number of carriers are also very high. And then if 1 by t increases, if you go here in this direction, 1 by t increases. If 1 by t increases, that means t decreases. And if t is decreasing, that means you are moving here. Basically in this graph, if you are moving here, that means in this graph you are moving here. So basically you are starting this graph from here. So how the graph will go? The graph will go somewhat like this. I will just draw the graph completely, and then you tell me whether you are able to relate or not. So this is how the graph will go. Say yes or no. This will be our 1 by t2, and this would be our 1 by t1. I hope you are able to relate this graph, how this graph is happening. If 1 by t is very low, that means t is very high. T is very high, that means a lot of charge carriers are there. Now if 1 by t increases, that means t decreases. If t decreases, that means you are moving here. So just this graph was made like this. Now you just go opposite. So increasing to decreasing, then constant, then decreasing. What I am saying, increasing to decreasing, constant, decreasing. So increasing to decreasing, constant, then decreasing. This is just, this graph just made opposite, because in the examination, usually in the textbook you will see that this graph is made. So that's why in the examination what they can ask, number of electrons versus 1 by t. They will not ask number of electrons versus t, they will majorly ask number of electrons versus 1 by t. Because in the textbook in Niemann this graph is made. Semiconductor Physics by Donald A. Niemann, one of the best book for EDC. In that particular book this graph has been made. So n versus 1 by t also you should be able to make. So usually in the examination what I will do is that I will make the graph of n versus t. Now if I need to make n versus 1 by t, what I will do, from here I will start and just make it opposite. So increasing, highest to decreasing, constant, then decreasing. So highest to decreasing, constant, and then decreasing. All good, all fine. So yeah, a very important graph, a very important, and I can expect that it is coming in the upcoming GATE examination very soon. Either this graph or this graph. Since it is given in the Niemann, so high probability is that they will ask this particular graph. Okay. So the complete theory is written. Let's read it. N-type semiconductor, 0 Kelvin, all donor atoms are neutral and electron will occupy the valence band. So the conduction band is completely empty and the electron concentration in the conduction band is essentially 0. At low temperature, 0 Kelvin, a very few electrons gain enough thermal energy to move to the conduction band. So electron concentration increases slowly. This is called freeze out region. In the mid temperature range, even though thermal energy is available to ionize most of the donor atom, so almost all the donor atom will contribute to the conduction. Here the electron concentration in the conduction band is roughly equal to the donor concentration Nd. Did you understand this point? At mid temperature what really happened is that all the donor atoms have been ionized. So started increasing, here it will become constant and is almost constant, forming the extrinsic region. So it is known as extrinsic region. At very high temperature, intrinsic carrier regeneration becomes significant because of the thermal energy. Because thermal energy is sufficient enough to excite the electrons from the valence band to the conduction band. So electron concentration will start increasing rapidly with temperature, and this is known as intrinsic region, where the conduction is dominated by thermally generated electron hole pairs. So you are able to understand every single line that has been written here. Say yes or no. Okay. Now the same plot you can draw for number of holes in the p-type semiconductor versus temperature. Although in our textbook this curve is given, but they can ask the same kind of plot for number of holes in p-type semiconductor versus temperature. So the same analogy you will make, 4 kind of graphs you will make, and you will be able to draw the graph. The same graph you will get. Initially what will happen? There are no holes. Slowly holes will start ionizing. Then what will happen? They will become constant, and after that, because of the thermal energy, they will start increasing rapidly. And if you need to draw it versus with respect to 1 by t, then this is how the graph will go. All good? All fine? Okay, so you can draw the graph on your own. Let's see the next graph. Before going to the next graph, we need to understand one term that is known as scattering. So you already know everything about scattering. What is scattering? Let's just say there is an electron. This electron has to move. Where it will be moving? It will be moving in the silicon crystal. So silicon, 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 silicon. There can be some impurity as well. Let's just say there is some donor impurity, or there can be some acceptor impurity as well, right? Acceptor impurity as well. And these atoms can vibrate as well. These atoms can vibrate as well, because if the atoms are getting thermal energy, then they will start vibrating. If atom will get thermal energy, then they will start vibrating. So this electron cannot move freely, right? Just as this electron gets into the crystal, it cannot move freely because atoms are vibrating. So what they will do? They will collide with the electron. These atoms and electron will collide. Or what may happen is that, like, somehow electron has reached here. So what will happen? This positive charge can attract this electron. So it will also affect the motion. And what may happen? Let's just say electron has reached here. So this negative charge can repel this electron. So this will also affect the motion, right? So electron is not moving freely. It is colliding, or it is being affected by some impurity or anything. This phenomena is known as scattering. So electron is getting scattered, right? Are you able to understand this point? And because of the scattering, what will happen? Mobility will decrease. Do you remember this point? That if there are a lot of these kind of phenomena, that electrons are, there is impurity, there is this lattice vibration. Because of that, what will happen? Impurity will decrease. Do you remember that particular thing? Okay. So when I was explaining you mobility, at that time also I told you that electrons cannot move freely. When I was explaining you effective mass, at that time as well I said the same thing, that electrons cannot move freely. So electrons are actually being scattered. So in one line, in one word, if you want to call this phenomena, that is known as scattering. So electrons will be scattering. So there are mainly two kind of scattering. So first let's remove it and read the definition of scattering. So scattering, in a semiconductor, electrons or holes move through the crystal, but they do not move in a straight line forever. They keep on bumping into the things like atoms, ions, or impurities. This bumping is called as scattering, and it will slow down their motion. Very simple thing. You understood the meaning of scattering. Now there are two kind of scattering. One is impurity scattering, and other one is lattice scattering. What do you mean by impurity scattering? So impurity scattering. Impurity means it will be coming because of the impurity. So we have two kind of impurity: donor impurity and acceptor impurity. Donor impurity is positively charged, acceptor impurity is negatively charged. So if an electron started moving, it was going, but this positive charge attracted the electron. So it is affecting the motion, and this negative charge will repel the electron. So this is also affecting the motion. So that's why the electrons are getting scattered. So the scattering that is happening because of these impurities, the scattering that is happening because of these impurities, that is known as impurity scattering. You understood? Now just tell me one thing, this scattering will be dominating at lower temperature or higher temperature? This scattering will be dominating at lower temperature. Why is that so? Because at low temperature means you are having low thermal energy. And if thermal energy is low, that means electrons are moving slowly. If electrons are moving slowly, then these positive charge or negative charge can attract or repel the electron. Let us say if I am moving very fast and there is some guy standing and he wants to attract me. If I am moving slowly, then he will be able to attract me. But if I move very fast, then he will not be able to attract me, right? He will be standing just there. I just need to pass in front of him. So he is just standing, I am just passing. If I am passing very slowly, so he will catch me, or attract me or repel me. But if I am moving very fastly, then he will not be able to attract me, right? So this is dominating at lower temperature. Impurity scattering, listen to my statement very carefully. Impurity scattering is dominating at low temperature only. As the temperature increases, impurity scattering decreases. As the temperature increases, because if temperature increases, then thermal energy will increase, electrons will move very fastly. If electrons are moving very fastly, then they will not be able to attract me, right? Basically, if I am electron, if electrons are moving very fastly, then these positive ions or negative ion will not be able to attract or repel the electron. So the effect of impurity scattering will be reducing with increase in temperature. Everything you are able to understand, right? So all these things you should keep on revising, otherwise you will be forgetting it, right? So everything I have explained, everything is written here as well. That's why I have made the notes in a manner that whenever you read the notes, everything will come to you. Or whatever the phenomena that I am explaining, in your notes you can write it down in some side, right? Let's just say I explained why that if I am moving very fastly, then they will not be able to repel or attract me. So you can write it down in some brief manner, you can write it down in your notes only. Okay, so let's read the definition. This happens when electrons collide with impurity atoms. In the semiconductor, these impurities have extra charge that can deflect the electrons. It can either attract it or it can repel it. Impurity scattering is stronger at lower temperature because electrons move more slowly and spend more time being affected by the impurity electric field. Okay, is that clear to you? So it is dominating at a lower temperature only. As temperature increases, the thermal energy will also increase. If thermal energy increases, what does that mean? Impurity scattering also decreases, right? So this is the meaning of, this is your impurity scattering. Other scattering is lattice scattering or phonon scattering. So here what will happen? Atom, silicon atoms are there. Electron tried to move. If you give high temperature, then what will happen? These atoms will start vibrating. these atoms will start vibrating. So this atom vibration happen because of the temperature only, and it happens at the higher temperature. On low temperature they will vibrate very slowly. Let's just say this is my hand, I keep this hand on fire, then what will happen? My hand will vibrate, no? But if temperature is very low, then it will vibrate very slowly. But if temperature is very high, then it will start vibrating more and more. As I keep on increasing the temperature, it will start vibrating. So similar thing will happen with the atoms. When you boil the water, what happens? When water is being boiled, so you would see that water will keep on vibrating, right? Similar thing will happen with the atoms. So as you give more temperature, it will start vibrating more. And since they are vibrating at their place, this electron will be colliding with them. This electron will be colliding with the vibrating atoms. Electron will be colliding with the vibrating atoms. And if it is colliding, that means it is affecting their motion. So this is known as phonon scattering, or it is known as lattice scattering. So here it would be written lattice scattering, but other name is phonon scattering. Okay, other name is phonon scattering. Okay, it is written. So lattice scattering or phonon scattering. So this happens when electron collide with the vibrating atom of the crystal lattice. At higher temperature, the atom vibrate more. So electrons are scattered more frequently because of the atoms the moving atoms act like obstacle in their path. Right, moving atoms, those silicon atoms, those are moving, they will be working as a hindrance in their path. This is why lattice scattering is more dominant at the high temperature. Did you understand this point? Lattice scattering is more dominant at the high temperature. Why is that so? Because as the temperature increases, vibrations will increase. Lattice vibration will increase. Lattice vibration means atom vibration. If lattice vibration is increasing, that means lattice scattering also increases. So two kind of things are there, impurity scattering and lattice scattering. So when the temperature was low, at that time lattice scattering was dominating. As the temperature started increasing, the effect of lattice scattering is being less, but the effect of impurity scattering is being less, but the effect of lattice scattering is increasing. Are you able to understand this point, what I am saying? Let's just say this is the temperature line. At lower temperature, impurity scattering is dominating, but lattice scattering is not dominating. As the temperature increases, the effect of impurity scattering is going down, but the effect of lattice scattering is increasing. And at higher temperature, only the lattice scattering will be dominating, because electrons will be moving very fastly. So impurity will not be able to attract or repel them. Is that clear to you? I hope you are able to understand. If you are listening to me with the clear mindset, then you will be able to understand. There is nothing tough. Otherwise, you will not be able to understand a single line. So in the best possible manner, I am giving the explanation, and in the easiest language, I have written the theory as well. So don't think that this theory is written by ChatGPT. You go to ChatGPT and ask them what is impurity scattering. They will write down very tough language. But it's me who will give prompt to ChatGPT again and again that this is how you reduce the complex part of your language. Then I give them prompt that this is how you should write down the language. So I like all these things, all this material is made after a lot of efforts. Okay, it feels like that, sir. Okay, just you go to ChatGPT, what is scattering? They will give the definition, you put it down, or you simply copy it from textbook. No, if I do that, then what will be the difference? Everything is written in the textbook. No, you can read the textbook, but all these will take a lot of effort. Only thing you need to do is that you need to listen to me carefully. That's it. Just listen to me carefully, and everything you will be able to understand. And notes are also there in the easiest possible language. Okay. So I will make sure that in the EDC, the most difficult part is that you don't get easy language. There are a lot of terms, sir. Lattice, electrons collide, impurity, low temperature, high temperature, then phonon, all these things are there. So what is the meaning of all these things? So slowly you need to build up the concept. So you are able to understand the meaning of every single thing now. Phonon means heat. From phonon you will just understand that heat. Look, when these atoms vibrate, when these atoms are vibrating, so this is known as phonon. And because of this vibration, heat is generated. So I will again explain the meaning of phonon when we study direct band gap and indirect band gap semiconductor. So at that time phonon word will again come into action, and that we will study in the next lecture. But as of now you ignore this word phonon. There are two things, photon and phonon. Photon and phonon. Photon means light, phonon means heat. That's it. Photon is light, phonon is heat. So as of now if you feel like that, sir, what is this phonon? So ignore this word as of now. You just remember it is known as lattice scattering. Okay. Other things are written. Temperature dependence. So impurity scattering decreases with temperature because electrons will gain more energy, they will move faster and are less affected by the electric field. Which electric field? Impurity is electric field. Impurity electric field means this is a positive charge, this is a negative charge. This is coming because of the donor atom, this is coming because of the acceptor atom. So this electric field I am talking about. And your lattice scattering will increase with the increase in temperature because at the higher temperature atoms will vibrate more. So if atoms are vibrating more, then electrons will be colliding more. If they are colliding more, that means they will be scattered more. So at higher temperature lattice scattering will increase, at lower temperature impurity scattering will decrease. As the temperature increases, impurity scattering will decrease. Now a very important part is about to come. Okay, very important part. In the beginning only I told you, because of the scattering mobility will always decrease. Because what is the meaning of scattering? Scattering means electrons are not able to move freely. They are not able to move in the straight line. That means they are being scattered. They are having some hindrance, or they are not able to move freely. That means because of the scattering, always mobility will decrease. Because of the scattering, mobility will always decrease. Is that clear to you? So this line I have written here. Scattering always reduces the mobility of charge carriers because every collision slows them down and make their motion less smooth. So if scattering increases, then mobility decreases. Now our task would be to draw the graph between mobility and the temperature. Try doing it on your own. A rough graph I am expecting, that it will increase, it will keep on increasing, it will keep on decreasing. What will happen? What do you think? Just think about two temperature range, low temperature range and high temperature range. Let's just say this is a temperature T1, this is a particular temperature T1. So before T1 you are thinking low temperature range, after T1 you are thinking high temperature range. So let's talk about low temperature range. From 0 to T1, you are going from 0 to T1. That means you are in the low temperature range. In low temperature range, who is dominating? Impurity scattering is dominating, right? So only you need to think about impurity scattering. Now in this low temperature range, if I am increasing the temperature, then what will happen? Impurity scattering is going down. That means this impurity scattering is going down. If scattering is going down, then what will happen? Mobility will increase. Here I have written that more scattering means mobility will decrease, and if scattering is less, then mobility will increase. Scattering will always reduce the mobility. So if scattering is less, then mobility will increase. So what really happened there? Think about it again with the clear mindset, otherwise you will not be able to understand. At lower temperature, who is dominating? Impurity scattering is dominating. So till T1 I will only think about impurity scattering. Okay. Now in the lower temperature, if I increase the temperature, then what will happen? Impurity scattering will go down. That means electron will not be affected by the impurity. So if scattering is going down, what does that mean? Mobility will increase. So in the lower temperature range, mobility will increase. Now you have reached a particular temperature. After T1 you will say that this is high temperature range. After T1 you will say that this is high temperature range, from T1 to infinity. So in high temperature, who is more dominating? Lattice scattering, right? Lattice scattering is dominating. Now in the higher temperature range, if I increase the temperature, then what will happen? If I increase the temperature, then lattice scattering will increase. If I increase the temperature, that means atoms will be vibrating more, and if they are vibrating more, that means there will be more hindrance. So lattice scattering will increase, and if lattice scattering is increasing, what does that mean? Mobility will go down. So after T1 at a particular temperature, mobility will go down. So initially it was supposed to go in this direction, and if I increase this graph, this was also supposed to go in this direction. But in the lower temperature range, impurity scattering was dominating. In the higher temperature range, lattice scattering was dominating. In the higher temperature range, if I increase the temperature, lattice scattering will increase, and because of that mobility will decrease. But in the lower temperature range, impurity scattering is dominating. In the lower temperature range, impurity scattering is dominating, and in the lower temperature range, if I increase the temperature, impurity scattering will decrease. That means mobility will increase. So this is how the graph should have gone, and in between this temperature, both of the scatterings are dominating. Like at the mid temperature, both of the scatterings are dominating. So this kind of graph you will get. Arey bhai yaar. So this kind of graph you will get. So I'm not going to write down anything. It's just that you need to think about it. If you are not able to think about it, then at least mug up this graph. The graph will go like this. That's it. Just remember it. If you are not able to understand, hopefully you should be able to understand, because I have spent roughly around 20 to 25 minutes just to explain all these phenomena and only this graph. Our target was to make this graph only. Just to make this graph, I had to explain everything, all these things. So just to make this graph, we have understood these scattering, like impurity scattering, lattice scattering, and how it is depending on the temperature. And based on that, I hope you should be able to draw this graph on your own. So in the low temperature range, with the increase in temperature, mobility will increase. But in the high temperature range, with the increase in temperature, mobility will decrease. What is this high temperature? What is this particular temperature T1? It could be 100 Kelvin. For some, it could be 200 Kelvin. But for any material, it will never be greater than 300 Kelvin. What I am saying? For any kind of material, it will be always lesser than 300 Kelvin. This temperature T1 that I have written, it could be 100 Kelvin. For some material, it could be 200 Kelvin. For some material, it could be 300 Kelvin. It will never be greater than 300 Kelvin. So if I am at the room's temperature, by default, I will be at the room's temperature only. If I am at the room's temperature and I try to plot mobility versus temperature graph, what I will see? That just as I increase the temperature, my mobility will decrease only. Are you able to understand what I am saying? A very important point. This temperature T1 will depend on the material. For some material, it would be 100 Kelvin. For some material, it would be 200 Kelvin. But for none of the material, it would be greater than 300 Kelvin. That means for none of the material, it would be greater than room's temperature. So if I am at the room's temperature, which is by default, you will be at the room's temperature only. So if I am at the room's temperature and I try to increase the temperature of my room and I see how my mobility is going, so what do you see? Mobility will decrease. Say yes or no. Are you able to understand this point? So with the increase in temperature, mobility will decrease only if you are at the room's temperature or if temperature is not given. By default, if you need to take one temperature, what that would be? That would be room's temperature. So at the room's temperature, if you are already at the room's temperature, and after that someone asks you what will happen to mobility if you increase the temperature, then it will decrease only. So with the increase in temperature, mobility will decrease after the room's temperature, and before the room's temperature, it can increase. So this relation is, here mobility is proportional to T to the power 3 by 2, minus 3 by 2. Why minus 3 by 2? Because with the increase in temperature, mobility is decreasing, and here it will be proportional to T to the power plus 3 by 2. With the increase in temperature, mobility will increase. So mu is proportional to T to the power 3 by 2, and here it is proportional to T to the power minus 3 by 2. Is this graph clear to you or not? Okay. Shall I repeat everything that I said? Or you can go back to the video and watch it again. Again, in a quick manner, I will repeat. In low temperature range, impurity scattering is dominating. In low temperature range, if I increase the temperature, then impurity scattering will go down. Why impurity scattering is going down? Because electrons are moving faster and they are not being affected by the impurity electric field. That's why impurity scattering is going down. If impurity scattering goes down, then mobility increases. After a particular temperature T1, in high temperature range, lattice scattering will be dominating. The atoms will be vibrating at their place, and since they are vibrating, electrons will be colliding with those vibrations. as the temperature increases, the vibration will increase more. Electrons will collide more. That will increase the scattering, and since the scattering is being increased, mobility will decrease. That's it. This is the explanation. Within 1 minute, you will be able to revise it. By default, we will be at the room temperature only. So as the temperature increases, scattering will always decrease, by default taking room temperature. I have drawn the graph of mu versus T. You draw the graph of mu versus 1 by T. Mu versus T goes in this direction, mu versus 1 by T will go in this direction. So what will be the nature? This will be the nature only. The same kind of nature you will get, right? So in a rough way, I have drawn the graph, because in the examination they can ask the graph of mu versus 1 by T as well. Okay. Same graph you will get, no? From decreasing to increasing and then decreasing. From decreasing to increasing and then decreasing. So from decreasing to increasing and then decreasing. So low to high and then decrease. Low to high and then increase. Sorry. Low to high and then decrease. Low to high and then decrease. You will be able to relate it, or you can think that if 1 by T is low, that means temperature is high. So you can think in this phenomena as well, or just I have told you a trick that just go opposite in the graph. Low to high and then decreasing. So low to high and then decreasing. So this will be the graph of mu versus 1 by T. So anything they can ask, mu versus T also they can ask, mu versus 1 by T also they can ask. In some textbook, if you find that, sir, always in the textbook, sir, I saw that this was the graph given. So they are considering that they are starting from some particular temperature. They are not starting from 0 Kelvin. They might be starting from some 100 Kelvin or some 200 Kelvin or from room temperature. So with the increase in temperature, it will decrease only. It could be anything. For different material, it will be different. 0 Kelvin means minus 273 degrees Celsius. So they might not be starting from minus 273 degrees Celsius. They might be starting from minus 100 degrees Celsius. So after that, it will always decrease. Because this T can be 100 Kelvin as well. What is the meaning of 100 Kelvin? 100 Kelvin means minus 173 degrees Celsius. Right? So it is different with respect to different materials. Right? And with respect to different conditions as well. It will depend on doping and all these kind of things as well. Okay, so it can be different, but it will never be greater than room temperature. So no matter whatever the semiconductor that you are having, if you are at the room temperature, then always with the increase in temperature, your mobility will decrease. So what may happen is that in longer run, you might forget, sir, what this was. Because this is complete theory, no, this is not numerical. So in longer run, you might forget that, sir, what I studied. Then what you can do is that you can again come back to this video and revise it. What I am saying, in longer run, you might be forgetting, look, this thing you will not be forgetting. This graph you will not be forgetting in longer run. But this graph you will be able to remember that, sir, this was the graph. But how it came, I forgot, sir, at lower temperature, who was dominating, which was dominating, everything you will forget. And you will try to read the theory. It might happen that you are not able to understand the theory as well. It happens with EDC. Every time you study EDC, you will feel like that it is a new subject. This thing I have always said about EDC. Every time you study EDC, it will feel like that it is a new subject if you don't revise it. Revision is very important in the EDC. So if you, in the worst case, if you have already forgot it, then what you can do is that you can again come back and watch this video and you will be able to understand everything. Okay? Fine. So at low temperature, impurity scattering dominates because electron collide mostly with the dopant atoms. Mobility is low, but as the temperature increases, impurity scattering decreases with temperature. So mobility also increases. At higher temperature, lattice scattering dominates because atoms vibrate more. Mobility decreases with the increasing temperature since lattice scattering increases with temperature. Okay, well and good. Yeah, there is one more formula. So let's just say because of the lattice scattering, when you are considering only lattice scattering, at that time your mobility was mu L. When you were considering only impurity scattering, at that time your mobility was mu Im. When you were considering only surface scattering, at that time your mobility was mu surface. What is surface scattering, sir? You don't need to worry about that. Only two important things are there, impurity and lattice. Those I have explained. There could be a lot of different kind of scattering as well. Those you don't need to study. So with respect to different scattering, at some point of temperature, only lattice scattering will be dominating. At some point of temperature, only impurity scattering will be dominating. At some point of temperature, only surface scattering will be dominating. So because of only the lattice scattering, your mobility is mu L. Because of only the impurity scattering, your mobility is mu Im. And because of only the surface scattering, your mobility is mu surface. Now they ask you what is the total mobility. So for that this formula you need to apply. 1 by mu total will be 1 by mu impurity plus 1 by mu lattice plus 1 by mu surface and so on. Let's solve a numerical on this, you will be able to understand. Okay, so this is the numerical, although very rare chance that these kind of question they will ask. What they have given in a semiconductor, two scatterings mechanism are existing: surface scattering and phonon scattering. What is phonon scattering? Lattice scattering only. What is surface scattering? You don't know. Okay, surface scattering you don't know. If you want to know, like, because of the rough surface, electrons will not be able to move in a free manner, right? The surface could also be low. The surface could also be rough. So this is the scattering that will come because of the surface. Because of the rough surface, if electrons are not able to move in a good manner or in a perfect manner, then it is known as surface scattering. But you don't need to study about it. Just it is some kind of scattering that you don't know. So because of the surface scattering and phonon scattering, two kind of scattering are present. Because of the surface scattering, the electron mobility is 400. And because of the lattice scattering or phonon scattering, the mobility is 600. So effective mobility you need to tell. So what will be the effective mobility? So effectively I will use this mobility. So in some of the previous question you saw that sir electron mobility is mu n, some certain value was given, some certain value was given, mu p, some certain value was given. So they were giving this value at a certain temperature. So they have considered all these things, surface scattering, lattice scattering. After that they were giving this value. So that value 1 by mu would be 1 by 400 divided by 1 by 600. So you can simply do it. It would be from here 3 to 5 yeah, so value of mu will come out to be 240, right? It will be simply 400 into 600 divided by 1000. Yeah, so 240 centimeter square volt into second. So you can solve this equation, you will get the value of mu as 240 centimeter square upon volt into second. So this is your total mobility. All good. So very rare that these kind of questions will be asked, but still in some test series if you see these kind of problems you will be able to solve it. Just take the reciprocal and add it. Well and good. Okay. So this graph is also clear. Mu versus T graph is clear. N versus T graph is clear. P versus T graph is also clear. Number of holes versus temperature graph is also clear. And intrinsic carrier concentration versus temperature graph is also clear. So these graph we have seen. Now who comes into action? Carrier concentration done. Mobility done. Now who will come into action? Conductivity. So what you will see? Conductivity versus temperature graph for intrinsic semiconductor. So first we will see the conductivity of intrinsic semiconductor versus temperature graph. So what is the conductivity of intrinsic semiconductor? That is NiQ mu n plus mu p. Now how Ni is related with respect to the temperature? So that is some constant T to the power 3 by 2 e to the power minus Eg naught by 2 kT. Sir, Q is also a constant. A naught is a constant, Q is also a constant. So multiply with Q. What about sir mu n and mu p? Now sir, for mu we know two things. Mu is proportional to T to the power 3 by 2 and mu is proportional to T to the power minus 3 by 2. This will work in the low temperature range and this will work in the high temperature range. So mu is proportional to T to the power 3 by 2. So can I write down as mu is equals to mu naught T to the power 3 by 2 and mu is equals to mu naught, here mu naught 1 I am writing, here mu naught 2 I am writing, because I need to remove this proportionality sign. So if I remove this proportionality sign, some constant will come. So this is low temperature and this is high temperature. So no matter whether you put low temperature or high temperature, in both of the cases you will see that conductivity will increase with the increase in temperature. What I mean to say is that, let's just say I put a low temperature here. If I put low temperature, that means this formula I need to put. This formula I need to put. So what I will do is that Say yes or no. You agree to this point? So this we are doing at low temperature, right? This I am doing at low temperature. So what will happen is that T to the power 3 by 2 will come outside. T to the power 3 by 2 will come outside. So what I will be getting? A naught T to the power 3 by 2, 3 by 2, right? T to the power 3 by 2, 3 to the power 3 by 2, both will be added T to the power 3. A to the power minus Eg naught by 2 kt. Q is a constant, mu n naught, mu p naught, these are also constant. A naught is also a constant. So constant multiply with constant, multiply with constant. What you will get? Another constant. So this you are doing at low temperature. Low temperature. So let me know what really happened here. At low temperature as well, what do you see? At low temperature as well, what I see is that if your temperature increases, if temperature increases, this value will increase and this value will also increase. Why is that so? Because if temperature increases, this will decrease, e to the power minus x. X is decreasing, that e to the power minus x will increase. So your conductivity will increase only, right? So your conductivity will be increasing only. So at low temperature range also it is increasing. Let's check at high temperature. So at high temperature, what I will do? E to the power minus Ag naught by 2 kt q mu n naught T to the power minus 3 by 2 plus mu p naught T to the power minus 3 by 2. This is what you will do at the high temperature, right? Now T to the power minus 3 by 2 will come outside. T to the power plus 3 by 2 and T to the power minus 3 by 2. What that would be? T to the power 0. That would be 1 only. So A naught is constant, 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 constant. So everything is constant only. So what you are getting? Some B naught T to the power plus 3 by 2, T to the power minus 3 by 2, T to the power 0 only. So that term is gone. T to the power 0. That term is gone. What you are left with? E to the power minus Ag naught divided by 2 kt. So this is happening at high temperature. Here also you can see, if temperature increases, then this value will decrease, right? And if this value is decreasing, then whole value will increase. So even at the low temperature range or high temperature range, you put the values in the formula. In both of the cases, if temperature increases, your conductivity is increasing only. Now what kind of graph you will get, that is very complex. You cannot tell. Only the nature you can tell. So how I will make the graph? I will just make the graph in this manner. A very rough graph, that's it. What it shows? That with increase in temperature, mobility will increase. Sorry, not mobility. Sorry. With increase in temperature, conductivity will increase. That's it. Okay. Nature of the graph is not very straightforward. You can see that exponential relation is there, T to the power 3 relation is there. Here only exponential relation is there, so here you can make it, but in the low temperature range as well, it will be very difficult to make. So just I have made the graph in this manner. It is just telling that it is increasing, nothing else. That's it. So your conductivity with the increase in temperature is increasing. Is that okay for you or not? Conductivity of intrinsic semiconductor. So what I did, I wrote down the formula. Whenever it comes to conductivity or resistivity, what you will do, you will write down the formula. For Ni, what I did, I wrote down the formula with the concept as well, I explained it. For mobility, what I did, I explained the scattering and then I made the graph. When it comes to conductivity, what you will do, you will write down the formula. Whether it is for N type, P type, or it is for intrinsic. Always you will write down the formula. Now you know that this guy increases with temperature. What about these two guys? So these two guys are different. First they increases, then decreases. So both of the cases I consider. When I consider the both of the cases, I got to know that in both of the cases only, my conductivity is eventually increasing only. So Ni versus T when I am making, it will be a increasing graph. Okay. What will be the nature? We don't care. If 4 options are given, we will just see that in which graph my in which graph my conductivity is increasing. So that will be the answer. Okay. So yeah, this is the graph, but another point is there. Ln rho I versus 1 by T graph I will make. What will be the significance of the slope of this graph? What I am asking, what will be the significance of the slope of this graph? Temperature is not mentioned, so by default I will take room's temperature. Room's temperature. So what is the significance of the slope of ln rho I versus 1 by t? So first, can you comment that whether it will increase or decrease? Think about it and comment whether it will increase or decrease. Like the nature will be like this or it will be like this. And then what will be the slope representing? That also you need to tell. So let's write down the formula of rho I first. What is the formula of rho I? That is 1 by sigma I, and 1 by sigma I is 1 by ni q mu n plus mu p, right? Just 1 second, guys. Yeah, sorry for the interruption, guys. So where were we? We have written down the expression of rho I. We need to find out the slope between the curve of ln rho I versus 1 by t. Okay. So this is the expression of rho I. So what I will do is that first I will solve with respect to sigma I, because for sigma I have already written down the expression, and we need to go for room temperature, right? For the room temperature, high temperature means here room temperature only. So this expression we have derived for room temperature only, no? So we need to consider the case of room temperature. So at the room temperature, if I write down the expression of sigma I, that is ni q mu n plus mu p, right? Now what is the expression of ni? A naught t to the power 3 by 2 e to the power minus eg naught by kt q mu n plus mu p. What is the value of mu n? At room temperature. So for the room temperature, what will be the scenario? Mu n will be proportional to t to the power minus 3 by 2, because after the room temperature mobility will decrease only. Mobility will decrease only, right? So this is the expression that we are going to use. So mu n naught t to the power minus 3 by 2 plus mu p naught t to the power minus 3 by 2. So t to the power minus 3 by 2 will come outside, and this will get cancelled, and mu n naught, mu p naught, they will be constant only. So what you are left with? Some constant c naught e to the power minus q is also a constant, mu n naught, mu p naught also constant, a naught is also a constant, and t to the power 3 by 2 and t to the power minus 3 by 2 has been cancelled, right? So only you are left with some constant Eg naught divided by 2 kt. This is what you are left with. This is your sigma I. What will be your rho I? Rho I will be 1 by sigma I. That would be 1 by c naught. And if you take the reciprocal of e to the power minus x, reciprocal of e to the power minus x, what that would be? E to the power x. So 1 by c naught e to the power Eg naught by 2 kt, right? What is 1 by c naught? Again a constant. So can you write it down as rho I is coming out to be some constant, here a naught, c naught I have written. Let's write down the constant as b naught. Some constant e to the power Eg naught by 2 kt. What I need to do? ln rho I need to introduce. So both of the side I will take ln. Again ln b naught will also be a constant. What I am doing? ln b naught multiply with e to the power Eg naught by 2 kt. So ln m into n, what that would be? ln m plus ln n, right? So ln b naught plus ln e to the power Eg naught by 2 kt. So what do you see here? What you are getting? ln rho I is equals to ln b naught is a constant value that I am writing down as k naught plus ln and e will cancel each other. So what you are getting? Eg naught by 2 kt. So what do you see here? ln rho I versus 1 by t. What I need to do? ln rho I versus 1 by t. So what I can see here is that ln rho I Eg naught by 2k, Eg naught by 2k into 1 by t plus some constant. Isn't it like y equals to, this is our y axis, this is our slope, this is our x axis plus some constant. So this is the relation that I am getting. So what is our slope? This is the slope, right? The slope is representing Eg naught by 2k. 2k is a constant value, right? So the slope of ln rho I versus 1 by t represents the band gap. So if you know the slope of ln rho I versus 1 by t graph, then you will be able to know the band gap. So what is the significance? Significance is band gap. So if someone asks you with the use of the slope of L and y versus 1 by t graph, what you can find out? You can find out the band gap of the material. Are you able to understand this point? And now you can see that L and y versus 1 by t graph I am making. So if 1 by t increases, let's look at this particular expression. If 1 by t increases, 1 by t increases, not t increases, 1 by t increases. If 1 by t increases, so this 1 by t is increasing. That means this whole value will increase. Are you able to understand this point? 1 by t is increasing, not t is not increasing, 1 by t is increasing. That means actually t is decreasing. If 1 by t increases, that means t decreases. So if t decreases, then this whole value will increase. And now in e to the power x, if x is increasing, then this whole value will increase. So if 1 by t is increasing, then rho I will increase. Or you can say ln rho I will also increase. From this expression also you can see that if 1 by t increases, then this value will increase. Basically this whole term will increase. And if this whole term is increasing, then ln rho I will increase. So kind of this graph, you are not sure about the nature of the graph, but this is how you can make it. And if someone asks you at this point, if you draw the slope, at this point, if you draw the slope, what this slope will represent? So this slope m will represent Eg naught by 2k, where 2k, k is a constant, k, what is k? K is Boltzmann constant, right? 2 is a constant value. So what is this Eg naught? Eg naught is the band gap. So the slope of this particular graph is helpful in finding the band gap. This question has been asked in the examination 2 times. Ln rho I versus 1 by t graph. How it is useful? It is useful to find out the band gap. So if you just know this expression, if I have just explained you this particular graph, then would you be able to write down all these things? So don't mug up any graph. Are you going to mug up ln rho I versus 1 by t? It will be increasing. No, just write down the expression. Very simple mathematics it is. Very, very simple. So you will be able to do every calculation there, right? Let's see this question. Ln rho I versus 1 by t graph is given. Which semiconductor is having more band gap? Semiconductor A or semiconductor B? So you know that ln rho I versus 1 by t slope of ln rho I versus 1 by t curve represents the band gap. Right? So who is having more slope? A is having more slope, right? The slope of curve A is more than slope of curve B. I hope you know basics of signal system. This much basic you should know. This is the slope, this is the slope. Who is having more slope? If you move in this direction, the slope will keep on increasing, right? So the slope of A is more than the slope of B. If slope of A is more than the slope of B, what does that mean? Eg naught by 2k will be more than the, one second guys. Eg naught of A will be more than Eg naught of B. Yeah, so what I was saying, the slope here is more. Slope for curve A is more than the slope for curve B. If slope here is more, what does that mean? That means Eg naught of band gap of curve A will be more than the band gap of curve B. Right? Very, very simple thing. Very straightforward. Band gap is more. Okay. So from here you can see that ln y versus 1 by t will represent the band gap. If slope is more, that means band gap is more. So here the slope is more, here the slope is less. So if this slope is more, that means band gap of A will be more than the band gap of B. This is also a gate VIQ only. Okay, let's write down in a better manner. Band gap of A will be more than the band gap of B. And here I will write down Eg naught of A will be greater than Eg naught of B. Now this graph is very, very interesting. You need to keep your concentration again here, and then only you will be able to understand. What we are going to do? We are going to plot conductivity versus temperature graph only, but for n-type semiconductor. For n-type semiconductor, we are going to draw conductivity versus temperature graph. So for n-type semiconductor, n is mostly very, very greater than P. What does that mean? That means sigma will be n q mu n mostly. Say yes or no. So you know the graph of n versus t, you know the graph of mu n versus t as well. What I mean to say is that, have you drawn the graph of n versus t? Yes, where I have drawn? N versus t. This is the graph of n versus t. Have you drawn the graph of mu n versus t as well? Yes. This was the conductivity for holes as well, for the electrons as well. For both of them, the same graph will happen. And when it comes to conductivity, there is no difference between intrinsic or extrinsic. Intrinsic semiconductor or n-type semiconductor or p-type semiconductor, everyone will have the same mobility, right? All the holes will have the same mobility, all the electrons will have the same mobility. So here I did not say that it is intrinsic or extrinsic, but for the electrons, for electron concentration, here I said that it is n-type, right? Here I said that it is intrinsic. So here I have to differentiate between intrinsic and n-type, but when it came to mobility, I do not have to differentiate. Then I came to conductivity. So in conductivity, here we talked about intrinsic. So this was also about intrinsic only. Ln rho I. Rho I means intrinsic only. So everything is going for intrinsic only as of now in this particular scenario. Now we will move to extrinsic. So in extrinsic, we are talking about n-type semiconductor where n is very greater than p. So sigma is equals to n cube mu n. So do you know the graph of n versus t? Yes. So in a rough manner, I am making the graph. This is graph of n versus t. And do you know the graph of mu n versus t? Yes. So this was a certain temperature, and I am saying that at room's temperature, this thing is happening. After that, it is reducing. So where will be room's temperature? This will be the room's temperature, because you know that at room's temperature, most of the electrons will be ionized. Most of that donor level electrons will be ionized. So if this is the T1 temperature in this particular graph, then in this particular graph, this will be the T1 temperature. This T2 temperature is very high. This T2 temperature is very high. So this is the T1 temperature here, and this is the T1 temperature here, right? All good. So in the initial, what will happen? If the temperature increases, n also increases and mu n also increases. So both are increasing, so graph will increase only. Aggressively it will increase, right? After that, what is happening? After T1, here this is decreasing, mu n is decreasing, and this is constant. One factor is constant and one factor is decreasing. What does that mean? Decreasing graph multiply with constant. What does that mean? The graph will decrease only. After that, what is happening? Increasing graph and decreasing graph. I am talking about at T equals to T2. This is the T equals to T1 at room's temperature. But if the temperature becomes very high, so if the temperature becomes very high, then what will happen is that your semiconductor will become intrinsic semiconductor. And in the intrinsic semiconductor, the conductivity always increases. So conductivity will always increase. Did you understand this graph or not? Conductivity of n-type semiconductor we are putting. Conductivity of n-type semiconductor we are putting, which is n q mu. For n versus temperature graph, we already know. What is n? N is the concentration of electrons. So how the concentration of electron will increase with respect to the temperature? So first they will get ionized and then they will become constant. So when they are getting ionized, along with that mobility is also increasing. So this is how the graph is going. After a certain temperature, at a particular certain temperature, after that what is happening? After that temperature, mobility is decreasing, but your ionized concentration becomes constant. So mobility, this factor is decreasing, this is constant, Q is already constant, so this will decrease. At a very high temperature, what happens? At very high temperature, what it will become is that it will become intrinsic, right? What was this, John? This was the intrinsic, this was intrinsic region. What this was? This was the extrinsic region. And what this was? This was ionization region or freeze out region. So mostly your device will be working in this particular region. So for n-type semiconductor, your conductivity will decrease with increase in temperature. If temperature increases, your conductivity will decrease because you will be working in this extrinsic region only. This is the extrinsic region, and what this was? This was your ionization region. Did you understand this point or not? For T greater than T2, I am not writing down the theory for this. Okay, I am not going to write down the theory. You have to understand on your own. So what I will do is that I will make rough graphs so that you would be able to relate. So what I will do here, only I will make the rough graphs. So n versus T graph I will make, and mu versus T graph I will make. So n versus T graph if I make, I know that it will increase, then saturate, and then increase drastically. This temperature was T1 and this temperature was T2. And here at T1 temperature only, this was n versus T, and this was your mu n versus T. So here at till T1 temperature it increases, but after that it will decrease only. Always it will keep on decreasing. Always it will keep on decreasing. So it will just keep on decreasing. Mobility will keep on decreasing, because if temperature increases, the atoms will vibrate more, scattering will be more, and mobility will decrease. So here it will keep on decreasing, but after T2 temperature, what will happen? A lot of carriers will be there. A lot of carriers will be there. A lot of electrons will be there. And since there are a lot of electrons, then conductivity will keep on increasing. And we are actually going into intrinsic region. And for intrinsic semiconductor, we know that conductivity always increases with respect to the temperature. So basically this relation we will start to follow. So this kind of graph we will get. What about this graph? Versus 1 by T. So how will you start? From the top, go down. From the top, go down, and then again increase. I am working in this direction, right? When I am making sigma versus T, I will work like this. When I am making sigma versus 1 by T, now I will work like this. So from the top, starting from the top, go down. Starting from the top, go down. Once you have reached to the below point, then again you increase. Then again you increase. Then again you reach to a 1 point. Again you reach to 1 point. And after that, again you decrease. After that, again you decrease. So in this manner it will decrease. It will not decrease very drastically, slowly it will decrease. So this kind of graph you will get. Again, very important, very soon this graph is coming in your examination. Sigma versus 1 by T for n-type semiconductor, very soon it is coming, because it is given in Donald A. Neiman. And from that particular book, all the question comes. So whatever that is there, unsolved example, solved example, whatever that is there, whatever that is useful for us, everything we are going to study in this course. Don't worry about that. So you will not have to read that book, but whatever that is available in that particular book, I will make sure that comes in your notes. Okay, so this kind of graph is already given there, so surely it is coming in your examination very soon. Is that clear to you or not? All good? All fine? So yeah, I hope that graph is clear. Similar graph will happen for p-type semiconductor as well, that we are not making. For p-type semiconductor, what will happen? P, Q, mu P. So this graph will be same. Sorry, which graph? This graph will be same. In place of n, you just need to replace P, and mu P, this graph will also be same. So ditto the same graph you will get. Ditto same graph, everything will be same. So we are just studying for n-type semiconductor. For p-type semiconductor, everything will be same. Just in place of electrons, you will replace holes. That's it. Because their majority charge carriers are hole, not electrons. All good? All fine? So this graph is also done. Now mobility versus doping concentration. Mobility versus doping concentration. So this was our n-type semiconductor. So now what we are doing, we will just keep on increasing that doping. So let's understand with the example of n-type semiconductor. So what we are doing, more and more impurity we are putting. So if we put more and more impurity, what will happen? More and more positive charge will come. And if more and more positive charge will come, that means impurity scattering will increase. And if impurity scattering increases, or what may happen, a lot of atoms will also come. Like if I am putting Nd, that means I am putting more atoms. If more atoms are coming, that means phonon scattering will also increase. You are putting the impurity. If you are putting the impurity, that means because of the positive sign, what will happen? Impurity scattering will increase. You are putting the atom as well, right? You are putting the phosphorus atom. Because of that, what will happen? The phonon scattering the lattice scattering will also increase. So effectively, more atoms means more scattering. And if there is more scattering, what does that mean? Mobility will decrease. So mobility will decrease. There you go. Understood? More doping means more atoms. More atoms means more scattering. And if there is more scattering, what does that mean? Mobility will decrease. So scattering will always reduce the mobility. Scattering will always reduce the mobility. So this is what have been written. Initially from low to medium doping, impurity scattering keeps on increasing, so mobility falls. At very high doping, impurities are already everywhere. Adding more doesn't change much of scattering. So yeah, so scattering will saturate basically. If you keep on adding up, impurities, then already impurity scattering is already very high. So mobility will keep on decreasing, and then after that it will saturate. Almost it will saturate. Okay. Basically what I am doing is that I am adding up the impurities. More and more impurities. So at some point the impurity scattering will not be increasing more. Like already it would have reached to its peak. So if scattering has reached to its peak, that means scattering is not increasing more. it is already very high. That means mobility is already very low. So it will keep on decreasing, and after that it will, at some point it will saturate. Okay, so this kind of graph you will get. Just remember the graph, that's it. In the examination, what will happen is that they will make some graph and then they will ask which of the following graphs are correct. That's it. So mobility will decrease with respect to doping concentration. All good, all fine. Resistivity and conductivity versus doping concentration. So we have seen the mobility. We have seen the mobility. Now we are going to see resistivity and conductivity. So what is the formula of conductivity? This is conductivity, this is resistivity. That is NdQ, or you can write down NQ mu. NQ mu. We are taking the example of n-type semiconductor. Okay, we are taking the example of n-type semiconductor. Now someone will be saying that, sir, why you are not studying it for intrinsic semiconductor? We will not study these graphs for intrinsic semiconductor because doping concentration, doping will be done in extrinsic only, no? So you can study these graphs for n-type or p-type. This graph also for n-type or p-type. The graphs which could be understood for n-type, p-type and intrinsic, those are these graphs. So here sigma versus 1 by t, and here also you can see that sigma versus t. So this was for intrinsic, this was for n-type. Similarly also here also for mobility, for all three kind of semiconductor, the graph will be same. Intrinsic, n-type, p-type, for all of them mobility graph will be same. Here this was for n-type and this was for, this graph was for intrinsic. So intrinsic, n-type for everyone, intrinsic, n-type for everyone. For everyone means for n-type and p-type only, because we are looking at doping concentration. That means doping is done only in n-type and p-type. So this is the graph of mobility. Let's just say this is for n-type. This is for n-type. How will I make the graph for p-type? Will it be from here to here, or it will be from here to somewhat like this? Basically it will be starting from here more than this or lesser than this? Lesser than this, right? Because mu n naught value is always greater than mu p naught value, because mobility of electrons is greater than the mobility of holes. Right? In this graph as well you can do the same thing. In which graph? In this graph. If I say this graph I am making for electrons, if this graph I am making for electrons, then the graph of holes will go like this, or it will go like this. It will go like this, right? Because mobility of electrons are more than the mobility of holes. So here also you can say that, so this particular graph is for n-type semiconductor and this particular graph is for p-type semiconductor. Okay. Next, what we were seeing? We were seeing conductivity versus doping concentration. Conductivity versus doping concentration. So here I will make the graph only for n-type, not for p-type. Sir, why not for p-type? We will tell you later on. In the next lecture, you will understand why we are not drawing for n-type here. Sorry, why we are not drawing for p-type here. Okay, only for n-type we will draw. So what will happen? As the doping concentration increases, this n value will increase, right? As the doping concentration increases, this n value will increase, but this mu n value will decrease. This mu n value will decrease. As the doping concentration increases, this mu n value will increase and this value will increase. This guy is more dominating. Okay, who is more dominating? N is more dominating. So increasing is more, decreasing is less. Sir, why it is more dominating? Practically it is found that this guy is more dominating. So basically your conductivity will increase. And just think about it, no? If we are doping, why we are doping? To increase the conductivity only, no? So if we are doping, then conductivity should increase, no? And what about the resistivity? They are inverse of each other, so resistivity will decrease. A very rare chance that these graphs will be asked, because they are not completely correct. They are true only for n-type semiconductor. N-type. This is also true for n-type. Sir, why you are making it then? Because it is given in Niemann's book. That's why we are making it. Otherwise, I would have surely avoided this graph. Or some people will also have a doubt that, sir, if you have given the graph of mu versus doping concentration, why you did not give the graph for sigma versus doping concentration? Why you left that graph? It is given in the Niemann's book as well, and people will have a doubt as well. That's why I am making this graph. There is very rare chance that this graph will be asked, because for p-type semiconductor it would be different. In the next lecture we are going to study a topic which is called as minimum conductivity condition. So in that minimum conductivity condition, you will see that in p-type semiconductor, if I do the doping, so at a certain doping you will get the minimum conductivity, and after that it will increase. But in n-type semiconductor, always the conductivity will keep on increasing. Okay, why we were doping? We just go to the first lecture. In first lecture I told you why we are doping, because we wanted to increase the conductivity. So if we wanted to increase the conductivity, yeah, it will increase, right? So someone will say that, sir, with the increasing of doping concentration, mu n is going down. No, but n is increasing. So who is more dominating? N is more dominating. Sir, what is the reason? No reason. There is no particular reason that, sir, why n is dominating. No particular reason is there. It is just dominating, so it is dominating. This is what have been written here. At low doping, Nd is very small, so conductivity is very low. At moderate doping, Nd increases, so conductivity increases rapidly, even though mobility decreases somewhat. At very high doping, mobility drops strongly due to impurity scattering, so conductivity rises slowly or even can saturate. Basically, at very high doping, what will happen is that this mobility can drop, right? This mobility can drop, but N will keep on increasing. So what may happen is that it can even saturate, or it may rise slowly, but it will never happen that conductivity is going down. What I am saying is that at very high doping, this mu n will rise, this mu n will drop significantly. At very high doping, this mu n will drop very significantly, but this n will keep on increasing. Again, this n is dominating only. Okay, so it will not happen that, sir, conductivity will decrease. No, conductivity will not decrease, but the rise will be slow. Rise may be slow. The rise may be slow. At very high temperature, the rise may be slow. Here it is rising rapidly, but at very high temperature, the rise may be slow. But it will never decrease, that I am telling. Here also, the decay may be small. The decay may be slow. But it will always be decaying. It will always be increasing. That's it. Is that clear to you? Look, these graphs are very practical. Like understanding it with respect to theory is very difficult. Although somehow we are understanding it. But these are very practical graph. For different material, different kind of graph you will be getting. But only thing is you can comment on the nature. The nature is always increasing. That's it. This is the nature. Here the nature is always decreasing. Why is that so? Because conductivity and resistivity both are inverse of each other. So in our book, in Niemann, these two graphs are made. That's it. So directly I have made these graphs. Okay. But very rare chance that this will be asked. So don't focus much on this. Focus on the previous graph that we have made. This graph is very important. This graph is very, very important. This particular thing is very important. This graph also very important. These graphs are very important. Scattering is also very important. These graphs are also important. So one of the graph can be asked. If they are framing good question from basic semiconductor physics, then they can ask questions on the graph. More graphs are there, but that we will see in the next lecture. Okay. So which graph is left? Vd versus mu e. This expression we have written. So Vd versus E graph I will make. Mu versus E graph I will make. So a few more graphs are left, but majorly whatever the graphs are there, that we have already seen. So don't feel like that, sir, how we will remember. Concepts are there. Try to remember the concepts. Okay. And these are some good concepts that, okay, for a particular temperature it will rise and then saturate and then again rise. So these are like good graphs. This graph is very good. This graph is also very good. And if you know these two graphs, then surely very easily you will be able to make the graph of conductivity as well. Similarly for intrinsic type of semiconductor. So I have spent more than enough time, 1.5 hours on these graphs. So I hope you would have understood everything. Just in the last graph here I said that it will increase always, but no, not always increase. Basically it will never decrease, it will always increase only, but the speed of increase may be slow. Okay, so what it is written is that at very high doping, mobility drops strongly. Mobility will drop strongly due to impurity scattering. So conductivity rises slowly or even can saturate. But notice the word rises. So it will always rise. It can saturate or it can rise, but it will never decay. So if this kind of curve is coming in the examination, you will only see that in which of the graph there is no decay. So if there is no decay, that answer will be correct. All good, all fine. let's meet in the next lecture. I hope there is nothing else. Yeah, let's meet in the next lecture, and in the next lecture we will see some graphs, and whatever the topic is left, that we are going to cover. After that we need to study Fermi direct distribution, and after that we will study low level injection and continuity equation, and after that our chapter will be completed. Okay then, yeah, so let's meet in the next lecture. Thank you very much. Happy learning.